Hello and welcome back to Learn When You Sleep, where the universe slows down to the pace of a quiet breath, and the biggest questions in existence become companions for the night. Tonight, we are going to do something a little different from what you might expect. We are not going to talk about the brightest things in the cosmos. We are not going to trace the blazing paths of supernovae, or linger on the fierce light of quasars, or stand in awe of the largest galaxies humans have ever photographed. Tonight, instead, we are going to go looking for the things that are easy to miss. The objects that drift through space without announcing themselves, that exist in numbers beyond imagination, that carry on quietly in the dark without needing anyone to notice them. You see, there is a habit that comes naturally to us as humans. We are drawn to brightness. We are drawn to the dramatic, to the visible, to the things that catch the eye and demand attention. When we look up at the night sky, we notice the stars that shine. We trace the planets that move. We remember the constellations that ancient people named and passed down through generations. And there is nothing wrong with that. Those bright objects are genuinely wonderful, genuinely important, genuinely worthy of our attention. But the universe, as it turns out, does not share our preference for the spectacular. The universe, in its quiet and indifferent way, produces far more of the subtle than the bright, far more of the cold than the blazing, far more of the dark than the luminous. And most of those subtle, cold, dark things are simply not part of the stories we tell about the cosmos. They have been, in a very real sense, forgotten. So tonight, we are going to remember them, not with urgency, not with the kind of energy that keeps you awake, but with the slow and gentle attention that these overlooked objects deserve. We are going to drift through the spaces where they live, learn something of what they are, and let the knowledge settle softly into the mind the way dust settles through still air. The universe is mostly subtle. That is the idea we will carry with us tonight. Mostly subtle, mostly quiet, mostly made of things that neither glow brightly nor announce themselves. And in that subtlety, as we will discover, there is a kind of beauty that is every bit as profound as anything the most dramatic star could offer. Before we begin, take a moment to settle yourself. If you are lying down, let your body sink a little more deeply into whatever surface is beneath you. If you are sitting, let your shoulders drop. Let your breathing slow. The journey we are about to take does not require any rushing. The forgotten objects of the universe have been drifting in their darkness for billions of years. They will wait patiently for us. Take a breath in and let it out slowly, and let us begin. Imagine standing outside on a clear night, far from the glow of any city, in a place where the sky truly opens up above you. The kind of sky where the stars are not just points of light but a field, a depth, a texture that you can almost feel pressing gently back against your gaze. It is a humbling thing to stand beneath a sky like that, and it is easy in that moment to feel that you are seeing everything, that the sky is showing you the universe as it really is, laid out in its full abundance. But you are not seeing everything, not even close. What you are seeing with your naked eyes on that clearest of nights is a carefully selected sample of the universe's most theatrical performers. You are seeing the stars that burn hot enough and bright enough and happen to be close enough to pour their light across the void and land on your eyes. You are seeing the survivors of a cosmic audition, the objects that made the cut for visibility, that passed the threshold for detection by the most remarkable instrument in the known universe, which is the human eye on a dark night. And most of the universe, quietly, did not make that cut. Think about what a star needs to do to become visible. It needs to be massive enough to ignite nuclear fusion in its core. It needs to sustain that fusion for long enough to be alive when your eyes happen to be looking. It needs to be close enough that its light has not thinned too far by the time it reaches you. and it needs to be unobscured by the clouds of gas and dust that drift through the galaxy like fog through a forest. These are demanding conditions, and the universe does not meet them for the majority of the objects it creates. For every star that you can see in the night sky, there are many more objects drifting nearby that produce little or no light of their own. Objects that began with some of the same ingredients as stars, but never quite crossed the threshold into true stellar burning. Objects that were flung out of their original homes and now travel through the dark without any sun to circle. Objects that are, in the strictest physical sense, galaxies, but that contain so few stars that they are effectively invisible. Objects so cold, so dense, so far from anything, that no telescope we have yet built can easily find them unless we look very carefully in exactly the right way. This is not a small gap in our picture of the cosmos. It is, in fact, the majority of the picture. The bright objects, the ones we know and name and chart and photograph, may represent only a fraction of what is actually out there. The universe's true population, its full census of objects, is dominated by things we cannot see with the unaided eye and have only recently begun to understand. There is something philosophically interesting about this. We have built our entire mythology of the cosmos around the visible, around the dramatic, around the things that draw the eye. Every culture that has ever looked upward has looked at the same bright stars, told stories about them, named them after gods and heroes and animals. And yet the objects those cultures never saw, the cold dwarfs and wandering worlds and dark galaxies, outnumber the bright stars perhaps by an enormous ratio. The universe, it turns out, has been keeping most of itself private. Tonight, we are going to gently intrude on that privacy. Not by forcing anything into view that does not wish to be seen, but by learning the language of the subtle, by developing an appreciation for the things that exist without brightness, that carry on without drama, that make up the quiet majority of a cosmos we have always, until very recently, imagined to be mostly ablaze with light. Each of the objects we will visit tonight has its own character, its own story, its own place in the physics of how matter organizes itself in the dark. And each of them, in its own way, will teach us something not just about the universe, but about the way we see it, about what we choose to look for, and about what we discover when we learn to look differently. Let your breathing continue to slow. Let the image of that clear night sky stay with you, but let it soften a little. Let the bright stars dim slightly in your mind's eye until the spaces between them begin to feel less empty. Because they are not empty. They are full of the forgotten. And we are about to meet them. Let us begin with perhaps the most abundant forgotten objects in the galaxy, the ones that outnumber bright stars, that drift through the Milky Way in numbers we are still trying to count, that exist in a space between categories that science spent a long time struggling to define. Let us begin with the brown dwarfs. The name itself is a small puzzle. Brown dwarfs are not, in fact, brown. If you could somehow see one up close, you would find an object that might appear deep red, or a kind of dull burgundy, or a muted orange depending on its temperature and composition. Brown was the name given to them before anyone had ever actually seen one, a placeholder color for something that was neither the blazing white or yellow of a true star, nor the dark completeness of a gas giant planet. The name stuck, even though it is not quite accurate, and so brown dwarfs they remain. What a brown dwarf actually is an object that sits in the boundary territory between stars and planets. In the universe, when a cloud of gas and dust collapses under its own gravity, the result depends very precisely on how much mass is involved. If there is enough mass, The core of the collapsing object becomes hot enough and dense enough to ignite hydrogen fusion, the process that makes stars shine. Hydrogen nuclei slam together with enough force to fuse into helium, releasing enormous amounts of energy as light and heat. That is a star. That is what our own sun is doing right now, fusing hydrogen in its core, releasing energy, pushing back against the gravity that would otherwise collapse it, shining. But what if there is not quite enough mass? What if the collapsing cloud produces an object that is, say, 13 times the mass of Jupiter, or 30 or 50, but still falls short of the roughly 80 times the mass of Jupiter that is needed to sustain hydrogen fusion? What happens then? What happens then is a brown dwarf, an object that forms the same way a star forms, that goes through the same early processes of collapse and heating, that may even burn briefly on a different kind of fuel, a heavier form of hydrogen called deuterium, for a short time in its early life, but an object that never crosses the threshold into true stellar burning, an object that glows faintly from the residual heat of its formation, from the slow release of gravitational energy as it contracts. An object that dims over time, cooling down decade by decade, millennium by millennium, until eventually it becomes one of the coldest, darkest, most invisible things in the galaxy. Brown dwarfs are, in the most poetic sense, almost stars. They are the universe's near misses. They gathered enough material to begin the process, to initiate the collapse, to form a round and coherent body with a real interior and an atmosphere and a surface of sorts. But they never quite lit the fire. For a long time, astronomers suspected they must exist. The mathematics of star formation seemed to suggest that the process of collapsing gas clouds should produce a range of masses, not just the masses heavy enough for full fusion. There should, the theory went, be objects below that threshold, objects that formed like stars but burned like embers. But for decades, no one could find them. Brown dwarfs, by their nature, are dim. They do not shine like stars. They radiate mostly an infrared light, the kind of light that is associated with warmth rather than visible brightness. And they are cold enough that even that infrared glow is faint. The first confirmed brown dwarf was discovered in 1995, and since then the count has grown considerably. Infrared telescopes, designed to detect heat rather than visible light, have found them scattered throughout the galaxy. Some orbit distant stars as faint companions. Some drift alone through space, having formed in isolation or having been ejected from their original systems. Some exist in pairs, two brown dwarfs circling each other in a slow gravitational waltz through the dark. And as the count has grown, something remarkable has become clear. Brown dwarfs are not rare. They may, in fact, be among the most common objects in the Milky Way. Some estimates suggest there are as many brown dwarfs in our galaxy as there are true stars, perhaps more. For every sun you can see in the sky, there may be a cold, dim, forgotten near star drifting somewhere nearby that no naked eye will ever find. That is what a brown dwarf is, an almost star, a patient, cooling, quietly abundant presence in the dark. And it is only the first of the forgotten objects we will visit tonight. Let that idea settle for a moment. For every bright star, a dim companion. For every visible light, a hidden warmth. The galaxy is fuller than it appears. There is a phrase that follows brown dwarfs wherever they are discussed, a phrase that has attached itself to them so persistently that it has become almost their unofficial name. That phrase is failed stars, and it is worth spending a little time with that phrase tonight, not to defend the brown dwarfs against it exactly, but to ask whether it really captures what these objects are, and whether the word failure means anything useful when we are talking about the physics of the cosmos. When we call something a failed star, we are applying a very human framework to a process that has no intentions, no goals, no ambitions to fulfill or fall short of. A brown dwarf did not try to be a star and fail. It did not set out to ignite hydrogen fusion and find itself unable. It is simply an object that formed with a certain amount of mass, and that mass was enough to make something remarkable, something with an interior and an atmosphere and a gravitational presence, and a lifespan measured in billions of years, but not enough to cross a particular physical threshold. The threshold is real. The fusion limit is a genuine feature of the physics, but the failure is our interpretation, not the brown dwarf's experience. Think about it from a different angle. Brown dwarfs have an extraordinary range of properties that make them fascinating in their own right, quite apart from any comparison to stars. The more massive brown dwarfs, those that sit close to the stellar boundary, can have surface temperatures of several thousand degrees and emit a dim reddish glow that is genuinely beautiful when observed with the right instruments. As brown dwarfs cool over millions of years, their atmospheres become extraordinary places. The chemistry of a cooling brown dwarf atmosphere is rich and strange. Water vapor forms, methane appears, iron and silicate particles condense out of the gas and form clouds, actual clouds made of liquid iron droplets or particles of sand, floating in the atmosphere of a cooling object smaller than a star but more massive than any planet. That is not nothing. That is not failure. That is a form of complexity and richness that the universe has produced through its own processes, and it deserves attention on its own terms. Some brown dwarfs have weather. Scientists studying nearby brown dwarfs with infrared telescopes have detected variations in brightness as the object rotates, variations that suggest bands of clouds moving across the surface, patches of clearer and cloudier atmosphere rotating in and out of view. The patterns are somewhat like the bands we see on Jupiter, but in an object that never became a star, floating in the dark far from any sun, experiencing its own internal weather driven by its own residual heat. Some brown dwarfs have companions, planets presumably, though distinguishing a brown dwarf's planets from those of a true star is a challenge for observers. If such planets exist, they would be in a very different situation from the planets of our solar system. They would orbit an object that provides very little light, that grows dimmer over time, that radiates mostly in the infrared. Whether any of those planets could support conditions interesting to life is unknown. The warmth of a young brown dwarf might, theoretically, provide enough energy. But as the brown dwarf cools, any warmth-dependent processes would slowly cease. Life, if it began there, would face a slow darkening. Brown dwarfs also occupy an interesting position in the question of what a planet is and what a star is. The boundary between a very large gas giant planet and a very small brown dwarf is genuinely blurry. Some objects of around 13 Jupiter masses can fuse deuterium briefly in their youth. Some objects just above that mass cannot quite manage even that. The categories we use, star, brown dwarf, gas giant planet, are human categories, clean lines drawn through a continuum that nature itself does not bother to honor. And this is part of what makes the brown dwarfs philosophically interesting. They sit at a boundary and refuse to neatly belong to either side. They are too dim to be stars, too large to be planets in the traditional sense. They are something in between, something that the universe produces abundantly, something that fits no clean category. And in their refusal to be classified tidily, they remind us that our categories are maps, not territories. The universe does not organize itself according to the names we give things. It simply proceeds, creating objects across a continuous range of mass and temperature and brightness, and leaves it to us to decide where one type ends and another begins. So perhaps instead of calling them failed stars, we might try calling them what they more accurately are: objects of the in-between, denizens of the threshold, or simply brown dwarfs, a name that does not quite describe their color but that has become their own, belonging to no other category of thing in the universe but them. Let that thought drift with you for a moment. The universe does not recognize failure. It only recognizes what is. And what is, in this case, is an abundance of warm, cooling, quietly complex objects drifting through the galaxy in numbers we are still learning to count. We have been talking about brown dwarfs as individuals, as objects with particular properties and temperatures and atmospheres and weather. But there is another way to think about them, and it is perhaps the most striking. We can think about them as a population. We can ask not just what they are, but how many of them there are, and what it means for our picture of the galaxy to have so many of them drifting through it unseen. The Milky Way contains somewhere between 200 billion and 400 billion stars. That is the number you hear most often when the galaxy is described. Hundreds of billions of suns, each a nuclear furnace, each pouring light into the surrounding dark, each a potential host for orbiting worlds. It is already an almost incomprehensible number, a population so vast that if every person alive on Earth right now began counting stars one by one, at a rate of 1 per second, each person counting for their entire lifetime, the combined total would not come close to the true number of stars in the galaxy. Now add to that count the brown dwarfs. Current estimates, based on infrared surveys and statistical modeling, suggest that brown dwarfs may exist in numbers roughly comparable to true stars. Some researchers have suggested the ratio could be close to 1 brown dwarf for every star in the galaxy, though the uncertainty is still large. Others suggest the numbers could tilt in either direction, depending on how star-forming regions behave at the low end of the mass spectrum. But even the more conservative estimates suggest that brown dwarfs are extraordinarily common. If the Milky Way contains 200 billion stars, and if there are even a comparable number of brown dwarfs, then we are adding another vast population to the galaxy's census. 200 billion cold, dim, slowly cooling objects drifting through the same space as the stars, invisible to the naked eye, detectable only with the right instruments, going about their quiet existence without anyone, for most of human history, even knowing they were there. Take that in for a moment. For most of the time that humans have been looking at the night sky, for most of the thousands of years that people have been mapping stars and naming constellations, and building their mythologies and their calendars around the movements of the visible cosmos, there has been an entirely parallel population of objects drifting through the same galaxy, in comparable numbers, completely unknown and completely unseen. The stars were the whole story as far as anyone knew, but the whole story was only half the story. And this is not unique to brown dwarfs. Brown dwarfs are simply the first example of a pattern we will encounter again and again tonight. The visible universe is a minority of the actual universe. The things we can see, even with our best telescopes, are not the whole population of what is out there. They are the tip of an iceberg whose base extends far down into darkness. Brown dwarfs are also interesting in the context of our own cosmic neighborhood. The nearest star to our Sun is Proxima Centauri, a red dwarf star about 4 light-years away. But it is entirely possible, some astronomers suggest it is likely, that there are brown dwarfs even closer to us than Proxima Centauri. Cold, dim, slowly radiating objects that are technically our nearest neighbors in space, but that have not yet been found because they are so difficult to see. A survey called the WISE mission, which surveyed the sky in infrared light, found several brown dwarfs within about 20 light-years of Earth, objects that had been sitting in our cosmic backyard for billions of years without anyone knowing they were there. One of those brown dwarf systems, a pair of brown dwarfs called WISE 1049-5319, and known more affectionately in the astronomical community as Lumen 16, is only about 6.5 light-years from Earth. That makes it the third closest known system to the Sun, third closest, and we only confirmed its existence in 2013, a neighbor that has been there since before our solar system formed, sitting quietly within cosmic walking distance, and we found it just a little over a decade ago. The quiet abundance of brown dwarfs, then, is not just a fact about the galaxy at large. It is a fact about our immediate neighborhood. The space around us is more populated than our star charts have ever suggested. It is full of cold, dim objects going about their slow business in the dark, waiting, in some sense, for the technology and the attention to finally find them. As you lie here tonight, or sit in the quiet of wherever you are, consider this. The neighborhood around our solar system, the space that feels so empty and dark when we look out into it, may contain a number of brown dwarfs comparable to the number of true stars. Objects with their own complex atmospheres, their own iron clouds, their own slowly fading warmth, drifting in the spaces between the stars, close enough in cosmic terms to be called neighbors, and almost entirely forgotten. That is the quiet abundance of the brown dwarf, not spectacular, not blazing, not demanding of our attention, simply present in vast numbers, patiently existing in the way that most of the universe exists, without needing to be seen to be real. Rest with that for a moment. The dark around us is not empty. It is full. Now we leave the brown dwarfs behind, those patient, cooling almost stars drifting through the galaxy in their quiet abundance, and we move to something that may feel even stranger. Something that, once you understand it, has a quality almost like a story, like a narrative of loss and wandering that echoes in an unexpected way. We move now to the rogue planets. You are familiar with planets, at least in the general sense. A planet is a world that orbits a star. It is defined in our common understanding by its relationship to a sun. The Earth orbits the sun. Mars orbits the sun. Jupiter, Saturn, Uranus, Neptune, all of them orbit the sun, each at their own distance, each completing their slow circuit in their own time. The planet and the star belong together, in the way that the moon and the Earth belong together. There is a gravitational bond, a permanent relationship, a center around which the planet perpetually moves. But what if a planet loses its star? What if a world fully formed, with its own geology and its own atmosphere and its own chemical history, is somehow torn away from the star it formed around and sent drifting off into space with no orbit to follow, no sun to circle, no light to receive? That world is called a rogue planet. And it is one of the most extraordinary and most overlooked categories of object in the universe. The name rogue carries exactly the right connotation. It suggests something that has broken free from the rules, that is operating outside the established order, that moves without the constraints that govern the behavior of ordinary planets. And that is precisely what a rogue planet does. It moves through the galaxy not in the tight gravitational leash of a solar orbit, but in its own long, slow, independent path, circling the center of the Milky Way the way stars do, drifting between the stars, belonging to no system, answering to no sun. The idea of a rogue planet is not science fiction. Astronomers have been discussing the theoretical possibility of such objects for decades, and the observational evidence for their existence has grown considerably in recent years. The question of how many of them there are and exactly how they form and escape their original systems is still being actively researched, but the basic fact of their existence is now firmly established. Rogue planets are real. They are out there, and they may be extraordinarily numerous. To understand how a planet becomes a rogue, it helps to think about what a young solar system looks like. When a star forms from a collapsing cloud of gas and dust, the leftover material from that collapse does not simply disappear. It flattens into a disk around the young star, a swirling pancake of gas and dust and rocky particles that gradually, over millions of years, collects into larger and larger clumps. Those clumps become planetesimals, and those planetesimals gradually collide and stick together to form the early planets. But this process is not orderly, it is chaotic. The young planets interact gravitationally with each other, and with the remaining gas of the disk, and with the star itself. Orbits shift. Planets migrate inward or outward from where they formed. In many systems, the gravitational interactions between young planets become so complex and so violent that one or more planets are ejected entirely, flung outward from the system with enough velocity to escape the star's gravitational pull. Imagine the chaos of those early solar systems. Young planets, still forming, still gathering mass, interacting with each other in a gravitational dance that is less a waltz and more a collision. In that chaos, it is not surprising that some planets lose the dance entirely, that they are flung out, sent spinning into the dark, cut off from the warmth and light of the star around which they formed. And once a planet is ejected, once it crosses the threshold of escape velocity and leaves its star behind, it is a rogue. It will drift through interstellar space for billions of years, or until some other gravitational interaction changes its path, cooling slowly, moving in its own arc through the galaxy. A world without a sun. That image, a world without a sun, is worth sitting with, because it is a world in the fullest sense. A body with mass and gravity and possibly an interior that still radiates heat from its formation. A body that formed the same way the Earth formed, from the same kinds of collisions and accretion and chemical sorting, but a body that is now entirely alone in the dark between the stars. Let that image form gently in your mind. A world drifting, dark but not empty, alone but real. The story of how rogue planets form is not a single story. There are several different paths by which a world can find itself untethered, and each of those paths tells us something different about the chaotic and sometimes violent processes by which solar systems shape themselves. Tonight, let us walk slowly through those paths, not to overwhelm the mind with complexity, but to appreciate the variety of ways in which the universe produces wandering worlds. The first and most commonly discussed origin for rogue planets is ejection from a forming solar system, the process we touched on in our last reflection. In the early life of a planetary system, the gravitational interactions between forming planets can be extraordinarily complex. Computer simulations of young solar systems show that in many cases, the dynamic instabilities of that early period cause one or more planets to be flung out. The most common scenario involves a close gravitational encounter between two large planets. When two massive worlds pass near each other, one can gain energy at the expense of the other. The one that gains enough energy exceeds the escape velocity of the system and departs. The other, having lost energy, falls inward. The system reaches a new equilibrium, but at the cost of losing one of its members to interstellar space. This process is thought to be common. Simulations of solar system formation suggest that a significant fraction of planetary systems eject at least one planet during their early history. Some systems may eject several. The violence of the early solar system is not an exception to the rule. It is, in many systems, the rule itself. The orderly arrangement of planets we see in mature solar systems, planets in stable orbits, widely spaced, not crossing each other's paths, is often the result of a period of early chaos in which the unstable orbits were eliminated, either by collision or by ejection. Our own solar system went through something like this. There is evidence in the structure of the outer solar system, in the strange distribution of objects in the Kuiper belt, in the arrangement of the giant planets, that early in the solar system's history, there was a period of significant gravitational upheaval. Some models suggest that the solar system may have originally had more giant planets than it currently does, and that one or more of them were ejected during this early turbulent period. If that is right, then somewhere in the galaxy, there may be a rogue planet that once belonged to our own solar system, that formed in the same disk of material as Earth and Jupiter and Saturn, that may have circled our sun for tens of millions of years before being cast out. But ejection from a forming system is not the only way to become a rogue. Some rogue planets may not have started as planets at all, at least not in the conventional sense. There is a process by which very small, very dense clouds of gas can collapse on their own without first forming a star, producing a planetary mass object through direct gravitational collapse rather than through accretion around a parent star. Objects formed this way are sometimes called sub-brown dwarfs, or planetary mass brown dwarfs, and they blur the boundary between a very small brown dwarf and a very large rogue planet in a way that is familiar to us by now. Nature, as we keep discovering, does not honor our categories. There is also a third origin story, less dramatic than ejection, but no less interesting. Some rogue planets may have formed within a solar system and then been gradually nudged outward over millions or billions of years by the accumulated gravitational influence of other objects. Not a single violent encounter, but a slow drift, a gradual migration toward wider and wider orbits until eventually the planet's orbit becomes so large and so loosely bound that a chance encounter with a passing star, or with the overall gravitational field of the galaxy, is enough to sever the last thread connecting it to its home system. A slow departure rather than a sudden ejection. A world that did not so much escape as quietly slip away. Now, how many of these worlds are there? This is where the numbers become genuinely astonishing. In 2023, a team of astronomers using data from a gravitational microlensing survey, a technique that detects the brief brightening of distant stars caused by the gravity of an object passing in front of them, published results suggesting that rogue planets in the Milky Way may be extraordinarily numerous. Their analysis suggested there could be hundreds of billions of rogue planets in the galaxy. Some estimates go further still, suggesting that rogue planets could outnumber stars by a significant margin. If those estimates are correct, there could be more wandering worlds in the Milky Way than there are stars to orbit. Let that sit for a moment. More planets than stars. A galaxy in which the majority of planetary mass objects have no sun, no orbit, no home system. a galaxy in which the wandering worlds outnumber the anchored ones. If this is true, and the uncertainty in these estimates is still significant, then the picture of a universe full of solar systems, each a tidy arrangement of planets around a central star, is fundamentally incomplete. The universe also contains, perhaps in even greater numbers, planets that belong to no system at all. Worlds adrift in the dark, moving through the galaxy in solitary arcs, carrying their geological histories and their chemical compositions and their cooling interiors through interstellar space for billions of years. The galaxy is not primarily a collection of solar systems. It may be, to a significant degree, a collection of lone worlds. Breathe with that idea for a moment. Hundreds of billions of planets drifting free. The universe's quiet majority, once again, hiding in the dark. There is a particular kind of stillness that comes with imagining the surface of a rogue planet. Not the stillness of sleep, exactly, but the stillness of total darkness, total cold, total isolation from the kind of light and warmth that we associate with the word world. Because if you were to stand on the surface of a rogue planet, you would find yourself in a situation unlike anything in the human experience of environments, unlike even the most extreme places on Earth, or the most hostile surfaces in our solar system. You would be standing on a world with no sun. There would be no sunrise, no daily rhythm of light and dark, no seasons driven by the angle of light falling on the surface. No photosynthesis, no solar wind, no ultraviolet radiation from a nearby star. The sky above you would be the sky of deep interstellar space, the same sky you would see if you were floating between the stars, an almost perfect darkness broken only by the distant points of other stars, none of them close enough to provide meaningful warmth, all of them so far away that their combined light would be less than the light of a full moon on a clear night on Earth. The temperature on the surface of most rogue planets would be extraordinarily cold. Without a star to provide energy, the only warmth available comes from the planet's own interior, from the residual heat of formation, and from the slow decay of radioactive elements within the rock. For a young rogue planet, recently ejected from its system, the interior might still be warm, might still be geologically active, might still produce enough heat to keep some processes going. But as billions of years pass, even that internal warmth fades. The surface temperature drops toward the temperature of deep space, which is just a few degrees above absolute zero. And yet, and this is one of the most remarkable things about rogue planets, even in that cold, even in that darkness, there may be places where things are different. Consider a rogue planet with a thick atmosphere. If a planet is massive enough, it can retain an atmosphere even without a star to provide energy, simply through its own gravity and the gradual outgassing from its interior. A thick atmosphere can act as a blanket, trapping the small amounts of heat radiating from the planet's interior and preventing it from escaping into space. The pressure and chemical composition of that atmosphere could, in principle, allow for temperatures at the surface or beneath it that are warmer than the surrounding space. Not warm by human standards, perhaps, but warmer, enough to raise the question of liquid water at some depth under sufficient pressure. There is also the possibility of subsurface oceans. We know from our own solar system that liquid water can exist beneath the frozen surfaces of worlds far from the sun. Jupiter's moon Europa has a liquid ocean beneath its icy crust, kept liquid by the tidal heating caused by Jupiter's gravity. Saturn's moon Enceladus has a subsurface ocean as well. These moons are in our outer solar system, receiving only a fraction of the sunlight that reaches Earth, and yet they have liquid water. A rogue planet, particularly a large one with its own internal heat, might maintain similar conditions entirely independently of any star. This possibility, the possibility of liquid water on a rogue planet, is genuinely significant. Because if there is one thing that the study of life on Earth has taught us, it is that life finds ways to exist wherever liquid water and chemical energy are available. Life has been found in the deepest ocean trenches, in hot springs, in frozen ice sheets, in acid pools, in the rock of deep mines. Wherever the basic conditions exist, life, or at least some form of microbial life, tends to appear. A rogue planet with a subsurface ocean would provide exactly those basic conditions: chemical energy from geological processes, liquid water, protection from the harshness of space by the overlying ice and rock. Now, we are not claiming that life exists on rogue planets. That would be a very large leap from what we currently know. But the possibility is not ridiculous. And the fact that it is not ridiculous is, in itself, a remarkable thing to consider. The universe may contain billions of wandering worlds, and some fraction of them may carry within their frozen interiors the conditions necessary for some form of existence. Not warmth-loving, sun-dependent life, not life that requires photosynthesis or seasons or the electromagnetic radiation of a nearby star, but life, perhaps, that is entirely internal, entirely geological, entirely independent of any star. Life that would be, in the truest sense, forgotten. Living in the dark interior of a world drifting alone between the stars, with no sun to orbit and no sky to look up at, sustained by the slow heat of its planet's cooling core, unknown to anyone, unreachable by any instrument we currently possess. Whether or not such life exists, the question itself is a reminder of something important. We have built our understanding of what makes a world habitable entirely around the example of Earth, around the framework of sunlight and warmth and liquid surface water. But the universe is not obligated to follow that framework. It produces objects across an enormous range of conditions, and some of those conditions may support processes that we would not intuitively describe as favorable, but that turn out to be sufficient for something remarkable to occur. The rogue planet drifts in the dark. Its surface is frozen, its sky is starless, and somewhere in its interior perhaps something is happening, or perhaps not. Perhaps it is simply a world in the dark, cooling, drifting, carrying its geological history through space for billions of years with nothing happening at all. Either way, it is real. Either way, it is there. Either way, it is part of the universe's quiet majority, and it deserves a moment of our attention. Let your mind rest on that image for a while. A frozen world, moving through the dark between the stars. Patient, ancient, forgotten, real. We have spent time with brown dwarfs, those almost stars that never ignited, drifting in numbers comparable to the stars themselves. We have visited the rogue planets, those wandering worlds unmoored from any sun, potentially numbering in the hundreds of billions. And now we come to something that stretches the imagination in a different direction entirely. Something that sounds, at first, almost like a contradiction, a paradox hiding in the language of the cosmos. We come now to dark galaxies. A galaxy, as we discussed in our last journey together, is a gravitationally bound system of stars, gas, dust, and dark matter. That is what the word means. And stars are the defining visible feature of a galaxy. When we photograph a galaxy, what we see is its stars, thousands or millions or billions of points of light arranged into a spiral or an ellipse or an irregular scatter. The galaxy is the stars, or so it seems. But what if a galaxy formed? What if the gas and dark matter gathered themselves into a coherent, gravitationally bound structure with enough mass to constitute a real galaxy? And then, for some reason, the stars never came. What if a galaxy went through the gravitational assembly process but skipped the step where the gas condensed into stars? What if there are galaxies out there, real galaxies in the structural sense, that contain little or no stellar light? Those would be dark galaxies, and there is growing evidence that they exist. To understand how a dark galaxy might form, it helps to think about what normally triggers star formation. Stars form when dense clouds of gas within a galaxy collapse under their own gravity. For that collapse to proceed all the way to a new star, the gas needs to be able to cool. Cooling is essential. When gas is hot, the pressure it exerts resists gravity, preventing collapse. But when gas cools, it loses pressure, and gravity can overcome the remaining resistance and pull the gas together tightly enough for nuclear fusion to eventually ignite. In most galaxies, this cooling process proceeds naturally. The gas clouds cool, they collapse, stars form, and the galaxy lights up. But there are conditions under which the cooling process can be disrupted. One important condition involves the spin of the dark matter halo that a galaxy forms within. If the dark matter halo is rotating very rapidly, the centrifugal effect of that spin can prevent the gas from collapsing to the density needed for star formation. The gas stays spread out, diffuse, unclumped, and no stars form. Another possibility involves the heating of the gas by intense radiation from nearby sources. In the early universe, the first stars and quasars produced enormous amounts of ultraviolet radiation that ionized the gas in nearby structures, keeping it hot, preventing it from cooling and collapsing into stars. Some theoretical models suggest that this early ultraviolet radiation may have suppressed star formation entirely in certain small structures, leaving them as dark or nearly dark galaxies. There is also a more dramatic mechanism. In dense galaxy clusters, the gas within smaller galaxies can be physically stripped away by the pressure of the hot gas that pervades the cluster. This process, called ram pressure stripping, can remove the star-forming material from a galaxy entirely, leaving behind only the dark matter halo, the stellar remnants of whatever stars had already formed, and possibly some residual gas that is no longer in a condition to produce new stars. The galaxy does not disappear. Its structure remains. Its dark matter halo persists, but its ability to make new stars is gone. Astronomers have found several candidate dark galaxies over the years, objects with the mass and structure of galaxies, but with far fewer stars than expected. One of the most discussed examples is an object called HI 1225+1, discovered in the 1980s through its radio emission from hydrogen gas. It appeared to have the mass of a moderate galaxy and an extended cloud of hydrogen gas, but almost no associated stellar light. Whether objects like this truly constitute dark galaxies in the purest sense, or whether they are extremely gas-rich low-surface brightness galaxies with a very small stellar population, remains a matter of ongoing research and debate. More recently, astronomers have discovered a class of objects called ultra-diffuse galaxies. These are galaxies that are enormous in physical extent, comparable in size to the Milky Way, but that contain extraordinarily few stars. Some ultra-diffuse galaxies discovered in galaxy clusters contain perhaps 100 times fewer stars than a typical galaxy of their size would be expected to have. They are not completely dark, but they are ghostly, so faint and so spread out that they had escaped detection, until relatively recently despite being located in well-studied galaxy clusters. One of the most remarkable of these is an ultra-diffuse galaxy called Dragonfly 44, discovered in 2016 in the Coma Galaxy Cluster. Dragonfly 44 is about the size of the Milky Way in terms of its physical extent, but it contains only about 1% as many stars. Almost all of its mass, about 99% of it, appears to be dark matter. It is, in a very real sense, a galaxy that is almost entirely dark. A gravitationally coherent structure, massive and real, with almost nothing to show for its size but an enormous invisible halo and a scattering of faint stellar sparks. Think about what this means. Dragonfly 44 has been sitting in the Coma Cluster, a well-studied cluster of galaxies not incredibly far from us in cosmic terms, for billions of years. Astronomers have been photographing the Coma Cluster since the early 20th century. And this enormous structure, a galaxy comparable in size to our own home, sat undetected in those photographs because it was too faint, too spread out, too subtle to notice without the specific kind of low-surface brightness imaging that was used to find it. How many others are out there? How many other ultra-diffuse, nearly dark, ghostly galaxy-scale structures are drifting through the clusters and filaments of the cosmic web, undetected because we have not been looking in the right way? The answer is almost certainly many. The discovery of Dragonfly 44 and others like it prompted a wave of new surveys specifically designed to look for low-surface brightness objects, and those surveys have found many more. The dark galaxies, or near-dark galaxies, are not rare exceptions. They may be a significant part of the overall population of galaxy-scale structures. The universe, once again, is hiding most of itself in plain sight. The dark galaxies drift in the clusters alongside their brighter neighbors, massive, ancient, real, and almost entirely invisible. They are perhaps the most dramatic example of the forgotten objects we are visiting tonight. Not just a forgotten type of star, or a forgotten category of wandering world, but forgotten galaxies. Entire structures of cosmic scale that we have only recently begun to find. Let that settle quietly. Galaxies without light. Real, massive, ancient, and almost entirely unknown until we learn to look with different eyes. We have looked at dark galaxies from the outside, at their extraordinary faintness, at their ghostly extent, at the way they drift undetected in galaxy clusters for billions of years, while brighter neighbors draw all the attention. But now let us step a little closer and think about what is actually inside these structures. What does a dark or nearly dark galaxy contain? What goes on within it? And what does the inside of a galaxy that never fully lit up look like? The first and most dominant component of a dark galaxy is its dark matter halo. Dark matter, as we discussed in our earlier journey through the cosmos, is the invisible substance that makes up the majority of mass in most galaxies. It does not emit light. It does not absorb light. It reveals itself only through its gravitational influence on the things around it. And in a dark galaxy, dark matter is not just the majority of the mass. It may be essentially all of it. When astronomers measure the mass of an ultra-diffuse galaxy like Dragonfly 44, by observing the motions of the few stars it contains, they find that the total mass is far greater than the mass of those stars could account for. The stars are essentially tracers, floating in a vast invisible sea of dark matter that vastly outweighs them. So the interior of a dark galaxy is, in the most profound sense, a structure of dark matter. A gravitational well, a place where the fabric of space is curved by enormous invisible mass. a region that is defined more by what it contains that cannot be seen than by what it contains that can be. But dark matter is not the only thing inside. Many dark and ultra-diffuse galaxies also contain gas, sometimes enormous amounts of gas. One of the signatures that has been used to identify dark galaxy candidates is the presence of hydrogen gas detected through its radio emission. Hydrogen gas, even when it is not forming stars, emits radio waves at a characteristic frequency, a wavelength of about 21 centimeters that radio telescopes can detect across vast distances. Some dark galaxy candidates have been found precisely because they have enormous clouds of hydrogen gas that are not associated with any obvious visible galaxy. The gas in these structures is cold and diffuse, spread out over vast regions, not condensed into the dense clumps that would be needed for star formation. It just sits there, organized by gravity, held within the dark matter halo, radiating its radio signature quietly into space. Gas that never became stars, raw material that was gathered but never used, the universe's unfinished business. There may also be a small number of globular clusters within dark galaxies. Globular clusters are dense balls of old stars that orbit galaxies as satellites. They are among the oldest structures in the universe, formed in the early epochs when the universe was young and dense, and star formation was much more vigorous. The presence of globular clusters in ultra-diffuse galaxies is one of the clues that these are genuine galaxies rather than some other kind of object. A real galaxy, even one that formed very few stars overall, would be expected to have some globular clusters. And the detection of globular clusters in objects like Dragonfly 44 is part of what convinced astronomers that these are indeed true galaxies, just extraordinarily dim ones. So inside a dark galaxy, we find an enormous invisible halo of dark matter, a diffuse cloud of cold hydrogen gas that never condensed into stars, and perhaps a sparse population of ancient globular clusters, relics of a brief period of star formation early in the galaxy's history before whatever process suppressed star formation took hold. And floating through all of this, perhaps a few thousand or a few million stars, so widely scattered and so faint that the galaxy appears essentially empty at casual inspection. It is a strange and rather haunting interior to imagine. No spiral arms crowded with young blue stars, no dense bulge blazing with the light of billions of suns, no active star-forming regions lit up in the pink and red of ionized hydrogen. Just dark matter and cold gas, and a handful of ancient stars spread thinly across an enormous volume, and silence, and time. There is also something interesting to consider about the fate of dark galaxies. Some ultra-diffuse galaxies are found in dense galaxy clusters, and those clusters are violent environments. The hot gas that pervades a galaxy cluster exerts pressure on any galaxy moving through it, and the gravitational tides of the cluster can strip material from smaller galaxies. For a dark galaxy, already deficient in stars and dense gas, the environment of a cluster may be particularly hostile. Over time, a dark galaxy in a cluster may lose more and more of its already sparse stellar content, becoming even more ghost-like, even more invisible, until it is essentially nothing but a dark matter halo with a few stray stars scattered across it. And then gradually those stray stars age and die. The massive ones explode as supernovae. The smaller ones swell into red giants and then fade into white dwarfs. One by one, over billions of years, the last lights of a dark galaxy go out. The dark matter halo remains. The structure, the gravitational well, persists, but the galaxy's brief and sparse stellar life is over. What remains is a dark matter structure, a gravitational signature with nothing to show the light. The most completely forgotten kind of forgotten object. Whether any galaxies have fully reached this state is unknown. The universe is old, but perhaps not yet old enough for the most ancient dark galaxies to have lost their last stars entirely. But the direction of travel is clear. Some structures in the universe are becoming darker with time, not brighter. Some galaxies are moving away from the visible, not toward it. The universe does not always trend toward light. Sometimes it trends toward a more complete and permanent forgetting. That thought is not a sad one, not really. It is simply honest. The universe produces structures at many different scales and of many different brightnesses. Some of those structures are blazing and obvious, and have been the objects of human attention and mythology for thousands of years. Others are faint and diffuse, and invisible to all but the most specialized instruments. And some are drifting toward a darkness so complete that they may never be found at all. And all of them are real. All of them are part of the universe's full inventory. All of them deserve, in their quiet way, a moment of acknowledgement. Rest here for a moment. In the interior of the dark galaxy, where the dark matter curves space around its invisible mass, and the cold gas drifts in clouds that will never become stars, and the last ancient globular clusters orbit slowly in the silence. It is one of the quietest places in the universe, and it is real. We have visited the almost stars, the wandering worlds, the galaxies that forgot to shine. And now we come to something that feels, in a very personal and almost tender way, like the most human of the forgotten objects. We come to the orphaned moons. A moon is, by definition, something that belongs to something else. It is a satellite. It is a companion. Its entire existence, in the common understanding, is defined by its relationship to the planet it orbits. Our own moon orbits the Earth, and that relationship is so fundamental, so woven into the fabric of life on this planet, that we simply call it the moon as though it were the only one. The moon raises our tides. The moon stabilizes the tilt of the Earth's axis. The moon has been the companion of this planet for 4.5 billion years, and in all that time, it has never been alone. But what if a moon lost its planet? What if the body that a moon had been circling for billions of years was somehow destroyed, or ejected, or disrupted, and the moon was left without an orbit to follow, without a gravitational anchor, without the planet that defined its existence? What would such a moon become? It would become, in the language of astronomy, a free-floating moon, an orphaned moon, a natural satellite that is no longer a satellite of anything. A body that formed as a companion and ended up alone. The idea of orphaned moons is newer in the astronomical literature than some of the other forgotten objects we have discussed tonight. It is a concept that has gained attention relatively recently, partly because of advances in our understanding of how planetary systems can be disrupted, and partly because of the same gravitational microlensing surveys that have given us our best estimates of the rogue planet population. Some of the objects detected in those surveys are ambiguous. They could be rogue planets, or they could be free-floating moons, or they could be very small brown dwarfs. The techniques for distinguishing between them are still being developed, but the theoretical case for orphaned moons is strong. The same processes that produce rogue planets can, under the right circumstances, also produce free-floating moons. If a planet is ejected from its solar system, its moons do not automatically travel with it. The ejection event, often a gravitational close encounter with another massive body, is violent and sudden. The planet may be flung outward so rapidly that its moons, which are held by the planet's gravity rather than the star's gravity, cannot stay bound. The moons may be scattered in different directions, some perhaps falling inward toward the star, some perhaps following the planet out into interstellar space, and some perhaps being flung off on their own independent trajectories, becoming orphans in the truest sense. A moon ejected in this way would become a rogue body in its own right. Smaller than most rogue planets but governed by the same physics, drifting through interstellar space, cooling, moving in its own long arc through the galaxy, and carrying within it the geological record of its origin. The chemical composition of a moon tells the story of what it formed from, what kind of planet it orbited, what kind of star illuminated it in its youth. An orphaned moon drifting through the galaxy is a small rocky or icy archive of a solar system that may no longer exist in any recognizable form. There is also a second pathway to becoming an orphaned moon, one that does not require any violent ejection event. Some moons may become free-floating simply because their parent planet was itself a rogue planet, a world that was ejected from its system, while its moons were still in orbit around it. In that case, the moons would initially travel with the rogue planet, still circling it in the dark of interstellar space. But the gravitational environment of interstellar space is not the same as the gravitational environment within a solar system. Out in the open galaxy, the gravitational tides and perturbations from passing stars, or from the overall structure of the galaxy itself, may gradually destabilize the orbits of the rogue planet's moons. Over millions or billions of years, those moons may drift away from their host planet, becoming free-floating objects in their own right. They began as moons of a planet, then they were moons of a rogue, and finally they became moons of nothing at all. The progression has a certain quiet sadness to it when viewed through a human lens. Although of course the moon does not experience sadness. It does not experience anything. It simply is. It simply drifts. And in its drifting, it joins the vast silent population of forgotten objects that constitute the universe's quiet majority. Let that image come to you gently. A small rocky or icy body, somewhere between a few kilometers and a few thousand kilometers across, moving through interstellar space. Once a companion, now alone, carrying its history and its craters and its composition and its slow internal cooling. Part of the universe's enormous, invisible population of solitary things. When we think about moons in our own solar system, we tend to think about the large and famous ones. Titan, with its thick orange atmosphere and its lakes of liquid methane. Europa, with its ice-covered ocean believed to contain more liquid water than all the oceans of Earth combined. Ganymede, the largest moon in the solar system, bigger than the planet Mercury. Enceladus, with its geysers of water ice erupting from cracks in its southern pole. Io, the most volcanically active body in the solar system, its surface constantly reshaped by the tidal heating it receives from Jupiter's enormous gravity. Each of these is a world in its own right. Each has its own geology, its own atmosphere where an atmosphere exists, its own internal dynamics, its own story. And each of them is, in some sense, defined by its relationship to its host planet. Europa's ocean is kept liquid by the tidal forces of Jupiter. Io's volcanism is driven by the same tidal forces. Titan's thick atmosphere is possible partly because of Saturn's distance from the Sun and partly because of Titan's own particular size and composition. The moons of our solar system are intimately shaped by the planets they orbit. Now imagine one of these moons cut free. Imagine Europa with its liquid ocean beneath the ice, drifting away from Jupiter and out into interstellar space. What would happen? Initially, not much. Europa's ocean would remain liquid for a long time, because the tidal heating would fade gradually as Europa moved away from Jupiter, and the ocean has enormous thermal inertia. But over millions of years, without the tidal heating, the ocean would begin to cool. Without Jupiter's gravity pumping energy into the moon's interior, the geological processes that maintain the warmth of the ocean floor would slow. Eventually, the ocean would freeze, starting at the top where it meets the ice shell and working slowly downward until the entire liquid reservoir was gone. Europa, the orphaned moon, would become a completely frozen body, its ocean a geological memory preserved in the chemistry of its ice. An orphaned version of Titan would lose something different. Titan's thick atmosphere is maintained by a continuous supply of nitrogen and organic compounds. Without the warmth of the sun, which is already very faint at Saturn's distance, the atmosphere would slowly freeze out, the nitrogen condensing onto the surface, the methane lake solidifying, the complex organic chemistry slowing and eventually stopping. Over millions or billions of years, an orphaned Titan would become a frozen, airless body, its remarkable chemical richness locked into ice and solid organic compounds. And yet, even in that frozen state, an orphaned Titan would still carry its chemical archive. Its surface and subsurface would contain a record of the organic chemistry that had occurred during its active years. Complex molecules, prebiotic chemistry, the building blocks of what might have been something more, all frozen and preserved in the cold. An orphaned Titan drifting through interstellar space for billions of years would be, in a very literal sense, a time capsule of chemical history. This is one of the more extraordinary ideas associated with orphaned moons. They are not just abandoned bodies, they are archives. They carry within their rock and ice and chemistry a record of where they came from, what they circled, what kind of star illuminated them, what chemical processes took place on their surfaces and in their interiors. If you could somehow intercept an orphaned moon and analyze its composition, you might be able to reconstruct something of the history of the solar system it came from. You might be able to identify the chemical signature of its parent planet. You might, in principle, find preserved organic chemistry or even preserved microscopic structures that speak to what conditions were like in its former home. The orphaned moon as an archive. As a message in a bottle, cast into interstellar space by the violence of planetary system dynamics, drifting for billions of years, carrying its contents undisturbed through the cold and the dark. There is also the question of what happens to orphaned moons much smaller than Titan or Europa. Most moons in our solar system are not the large, famous ones. Most are small, irregular bodies, chunks of rock and ice a few kilometers or a few tens of kilometers across, captured into orbit around a planet or formed from the debris of an ancient collision. These smaller moons would survive the ejection process as easily as the larger ones, perhaps more easily since their smaller mass makes them more susceptible to the gravitational perturbations that could send them off on independent trajectories. And so the universe may be populated not just with orphaned moons the size of Europa or Titan, but with an enormous number of smaller orphaned bodies, rocky and icy fragments of former solar systems, drifting through interstellar space in numbers that may vastly exceed the number of rogue planets. If rogue planets potentially number in the hundreds of billions, orphaned moons of various sizes might number in the trillions. A vast, invisible population of former companions, each carrying within it the chemical history of a solar system, scattered across the galaxy over billions of years of planetary dynamics. The Milky Way may be full of these small wanderers, small forgotten archives, pieces of worlds, remnants of systems, things that once had a place and no longer do, drifting in the dark between the stars, patient and silent and real. Notice how your own breathing has settled. Notice how the quiet of where you are mirrors in some small way the quiet of those drifting bodies, not the quiet of emptiness, the quiet of something that simply is without needing to announce itself. That is the orphaned moon, alone, ancient, carrying its history, part of the universe's vast unannounced abundance. We have been moving outward, in a sense, through the scales of the forgotten. From the brown dwarfs drifting between stars within a galaxy, to rogue planets moving through those same interstellar spaces, to orphaned moons wandering as fragments of former systems. And now, we make the largest leap yet. We move beyond the edges of galaxies entirely. We go out into the space between them, into that vast ocean of darkness that separates one galactic island from another. And we ask whether anyone could possibly be out there. And the answer, astonishingly, is yes. There are stars in intergalactic space, real stars, burning with nuclear fusion, shining with genuine light, far from any galaxy, drifting through the emptiness between galactic islands. These are the intergalactic stars, and they are among the most isolated objects in the known universe. To understand how a star ends up between galaxies, we need to think about what happens when galaxies interact with each other. Galaxies are not static, isolated islands. They move through space, they pass near one another, they collide, they merge. And when two galaxies interact gravitationally, the results can be dramatic. The gravitational forces at play during a galactic collision or close encounter are not uniform. They vary across the extent of the galaxies involved, and the result of these tidal forces, these varying gravitational pulls across a finite object, can be spectacular. During a galactic interaction, long streams of stars can be pulled out of both galaxies and stretched into great arcs and tails that extend for hundreds of thousands of light years into the surrounding space. These stellar streams are visible in images of interacting galaxies. The antennae galaxies, two spiral galaxies currently in the process of merging, display enormous tails of stars that have been flung outward by the tidal forces of the interaction. The mice galaxies, another interacting pair, have similarly dramatic tails of stars stretching far beyond the main bodies of the galaxies. Some of the stars in these tidal tails are moving fast enough to escape the gravitational pull of the galaxy pair entirely. They are ejected, flung out into intergalactic space, never to return. They become intergalactic stars, exiles from their home galaxy, cast out by the violence of a galactic collision, drifting through the enormous void between galactic islands. There is also a second mechanism for producing intergalactic stars. In the dense cores of galaxy clusters, where dozens or hundreds of galaxies orbit within a relatively compact volume, the gravitational interactions between galaxies are more frequent and more intense than in less crowded regions. Over billions of years of these interactions, a significant fraction of the stars from member galaxies can be stripped out and added to a diffuse population of stars that fills the space between the individual galaxies within the cluster. This population is called the intracluster stellar population, and it is, by some estimates, an enormous component of the total stellar content of rich galaxy clusters. Astronomers studying galaxy clusters have found evidence for this intracluster light, a faint diffuse glow filling the space between the individual galaxies of a cluster. It is extremely low surface brightness, much harder to detect than the light of the individual galaxies themselves, but it is there. And it represents a population of stars that no longer belongs to any individual galaxy. Stars that were born within galaxies, that lived their main sequence lives while still part of a galactic community, but that were stripped away and now drift in the common space of the cluster, belonging to no single galaxy, but to the cluster as a whole. Some estimates suggest that in rich galaxy clusters, the intracluster stellar population may contain as many stars as all the individual cluster galaxies combined. Half or more of all the stars in a cluster may be drifting free in the spaces between the cluster's member galaxies. If those estimates are anywhere near correct, then the stars we see neatly arranged within visible galaxies are, in clusters at least, only half the story. The other half is scattered between them in a vast, faint, diffuse sea. And beyond galaxy clusters, in the true intergalactic voids between clusters and filaments, there are stars as well. Stars ejected during ancient interactions that happened long ago, still drifting on trajectories that have taken them out of any cluster, out of any filament, into the open spaces of the cosmic web. These are perhaps the most isolated stars in the universe. Stars so far from any galaxy that even if you were standing on a planet orbiting one of them, the nearest galaxy might appear as only a faint smudge in the sky, millions of light years away. Imagine what the sky would look like from a planet orbiting an intergalactic star. There would be no Milky Way band, no dense field of nearby stars, no neighboring stars close enough to appear as bright points of light. The sky would be almost completely dark. The nearest other star might be hundreds or thousands of light years away. Distant galaxies would appear as faint, barely visible smudges scattered across an otherwise empty sky. It would be among the loneliest views in the universe. The most isolated vantage point from which any world could possibly look out. And yet that star would be burning, fusing hydrogen, producing light, following the same physics that governs every other star in the universe. Its light would pour out into the intergalactic void, traveling for millions of light years without encountering anything, illuminating nothing, fading into the background radiation of the universe. A star shining for no one in the middle of nothing for billions of years. That is the intergalactic star, forgotten in the most complete sense, exiled beyond the boundaries of any galactic community, shining faithfully and invisibly in the dark. There is a word in the Portuguese language, saudade, that describes a kind of longing, a melancholy for something distant or lost, a bittersweet awareness of absence. It is one of those words that does not translate cleanly into other languages because the feeling it describes is too specific, too layered, to be captured in a simple equivalent. And when I think about intergalactic stars, when I try to imagine what it would mean to be a source of light so completely removed from everything else, I find myself reaching for something like that word. Not because the star feels anything, of course, but because the image itself carries a quality of profound and peaceful isolation that seems to deserve a name. An intergalactic star drifts through a void so enormous that the nearest other star may be millions of light years away. The nearest galaxy, millions more. It burns its hydrogen with the same physics as every other star, produces the same spectrum of light, follows the same life cycle. It is entirely ordinary in its stellar nature, but its location places it in a context that is extraordinary. The light of an intergalactic star goes, in almost every direction, nowhere. It travels outward into the void, crossing light years, then tens of light years, then hundreds, and encountering nothing. No interstellar dust clouds to scatter it, no planets to warm, no moons to illuminate, no other stars to interact with. Just the expanding sphere of photons, thinning as it spreads, growing fainter with every passing light year, until eventually it is indistinguishable from the cosmic background. One more tiny contribution to the diffuse sea of ancient light that fills the universe. But here is something worth pausing on. Although the intergalactic star's light seems to go nowhere, it actually goes everywhere. It travels in all directions simultaneously. And in some of those directions, after traveling for millions of light years, it eventually reaches a galaxy. It enters that galaxy's space and continues, crossing the thin outer regions of the galactic halo, passing through the halo's sparse population of stars, perhaps eventually crossing the disk of the galaxy, perhaps even reaching a planet. And if there is a sufficiently sensitive eye or instrument on that planet, the intergalactic star might appear as a faint, unremarkable point of light among the billions of other points. Its extraordinary provenance, its millions of light years of solitary travel, invisible in the data. Just another star in the field. This is one of the more quietly astonishing facts about light. Every time you look at a sky full of stars, some fraction of the points of light you are seeing are not stars within our galaxy. Some of them are intergalactic. Some of them have traveled for millions of years through the void between galaxies before arriving at your eye. The night sky is not a window onto our galactic neighborhood alone. It is a window onto a much larger cosmos, including the lonely stars between galaxies, whose light has crossed the greatest distances in the universe to be part of the scene. The population of intergalactic stars is difficult to count precisely. They are, by definition, spread across enormous volumes of mostly empty space, but astronomers have developed techniques to identify them. One method uses the properties of certain types of variable stars, stars that pulse in brightness with a regular rhythm, as distance indicators. If such a variable star is found with a brightness that places it far outside any known galaxy, it is likely an intergalactic star. Another method uses the spectra of individual stars in galaxy clusters to identify those that are not associated with any individual galaxy, but are instead drifting in the intracluster space. Through these methods, the intergalactic stellar population has begun to come into focus. In rich galaxy clusters, the intracluster stars have been confirmed as a real and significant population. In some clusters, the diffuse glow of these stars is bright enough to be detected with careful photometry, revealing a faint haze of light filling the space between the cluster's member galaxies. This intracluster light is one of the most striking visual manifestations of the forgotten stars, a ghostly luminescence spreading across millions of light years of cluster space, produced by billions of stars that no longer belong to any individual galaxy. The James Webb Space Telescope, with its extraordinary sensitivity to faint light, has provided some of the most detailed images yet of this intracluster light. In images of distant galaxy clusters, the faint glow between the galaxies is visible as a soft luminosity that follows no particular galaxy's shape, spreading and pooling in the gravitational landscape of the cluster. It is light from forgotten stars, rendered visible by the most powerful telescope humanity has ever built, revealing a population that has been drifting there for billions of years. But even beyond clusters, even in the true voids where no cluster structures exist, individual intergalactic stars may drift. Stars ejected from galaxies during interactions billions of years ago, traveling on trajectories that have carried them into the emptiest regions of the cosmic web. These are perhaps the most isolated of the isolated. Stars so far from any galaxy that the universe around them is nearly as empty as the space between the filaments of the cosmic web. The most profound forgetting the universe has to offer, and yet each one burns, each one produces light, each one is at the atomic level the same kind of object as our own sun, the same hydrogen fusion in the core, the same photons climbing outward through the stellar interior, the same surface convection, the same magnetic activity, the same stellar wind blowing outward into a void that offers nothing to blow against. The star does not know it is forgotten. It does not know it is isolated. It simply is what it is, doing what stars do, burning patiently in the dark, for billions of years, whether or not the universe is paying attention. There is something deeply calming about that image, the persistence of the burning star in the void, the faithfulness of the light that travels for millions of years whether or not it ever reaches anything, the ordinary physics proceeding in extraordinary isolation. Our own sun is fortunate in the sense that it burns within a galaxy, surrounded by hundreds of billions of other stars, its light reflected off 8 planets and countless smaller bodies, received by at least one world rich enough to notice it and reflect on its nature. But the intergalactic stars ask whether that context is necessary. They suggest that the burning continues regardless of the context. That light is produced whether or not it is received. That the universe proceeds with its processes without requiring an audience. And somehow, that is a comforting thought. The cosmos does not need our attention to continue. It burns and drifts and collapses and cools and expands in the populated regions and in the empty ones, in the bright galaxies and in the dark voids, with or without anyone watching. The intergalactic stars are the most extreme example of this principle, burning faithfully in the places where no one will ever watch. Let that thought accompany you as your breathing slows. Something is burning somewhere in the dark between galaxies, patient, alone, and entirely real. Every object we have visited tonight has been something that either never became what it seemed destined to become, or something that was separated from the context that gave it its original identity. The brown dwarfs never ignited. The rogue planets lost their stars. The orphaned moons lost their planets. The dark galaxies never lit up. The intergalactic stars lost their galactic communities. And now, in the final category of forgotten objects, we turn to something different. We turn to the things that stars leave behind when they die. The remnants, the afterimages of stellar lives, the objects that persist after the burning is done. A star lives by burning fuel. The fundamental process of stellar life is nuclear fusion, the combining of lighter atomic nuclei into heavier ones with the release of energy. Our sun is currently fusing hydrogen into helium in its core, a process it has been carrying out for about 4.5 billion years, and that it will continue for roughly another 5 billion. When the hydrogen in the core is exhausted, the sun will expand into a red giant, then shed its outer layers, and then collapse into a small, dense, cooling object called a white dwarf. That white dwarf will then persist, gradually cooling, for an almost incomprehensibly long time. But that is only one possible ending. Stars of different masses end in different ways, and each way leaves behind a different kind of remnant. Some remnants are well known, at least by name. Neutron stars and black holes have a kind of cultural presence in the popular understanding of the universe. But others are less discussed, less noticed, and in their quiet persistence, they constitute yet another category of the universe's forgotten majority. Let us begin with the white dwarf, because it is the fate of the majority of stars. Stars like our Sun, and all stars smaller than about 8 times the mass of the Sun, end their lives as white dwarfs. Since the vast majority of stars are less massive than 8 solar masses, this means the vast majority of stars will eventually leave behind white dwarfs. A white dwarf is not a star in the active sense. It is not fusing anything. It is simply a dense, hot ball of carbon and oxygen, the ashes of stellar nuclear burning, held up against further gravitational collapse by a quantum mechanical pressure called electron degeneracy pressure. It is compressed, roughly the mass of the Sun packed into a sphere about the size of the Earth, but it is not burning. It is simply cooling. When a white dwarf first forms, it is extraordinarily hot, the exposed core of a former star, with surface temperatures in the hundreds of thousands of degrees. It glows brilliantly, not from fusion but from residual heat, like an ember that was once part of a fire. But it is cooling, and without any internal energy source to replenish the heat it radiates away, it will cool continuously over billions of years, slowly dimming, slowly reddening, slowly fading. At some point in the extraordinarily distant future, a white dwarf will cool to the point where it no longer emits any significant light. It will become what astronomers call a black dwarf, not to be confused with a black hole. A black dwarf is simply a white dwarf that has cooled completely, a cold, dark, inert sphere of compressed carbon and oxygen, floating in space with no light, no heat, no activity of any kind. A perfectly preserved remnant of a star, carrying within its structure the record of the nuclear burning that produced it, but entirely invisible and entirely quiet. And here is where the forgotten quality of these objects becomes most profound. The universe is not old enough yet for any black dwarfs to exist. A white dwarf takes roughly a quadrillion years, that is a 1 followed by 15 zeros, to cool completely into a black dwarf. The universe is only about 14 billion years old. So the first black dwarfs are still trillions of years in the future. But they are coming. The white dwarfs that exist today, all the billions of them drifting through the galaxy, are all on their way to becoming black dwarfs. They are slowly cooling toward a final darkness that will arrive in the unimaginably distant future. The white dwarfs themselves, though, are already among the forgotten objects in a practical sense. There are estimated to be somewhere between 10 billion and 20 billion white dwarfs in the Milky Way alone. That is an enormous number of stellar remnants, each the compressed core of a former star, each cooling quietly, most of them far too dim to see with the naked eye. We know of a few thousand white dwarfs through careful observation. The true population is thought to be billions. They fill the galaxy, these cooling stellar embers, remnants of stars that burned their fuel and faded, persisting in the dark long after their light is gone. Think about what each of those billions of white dwarfs represents. Each one is the remnant of a star that once burned for billions of years. Each one was once the center of a solar system, the source of warmth for any planets that orbited it, the gravitational anchor of a system of worlds. And now it is a cooling sphere, slowly fading, its system perhaps still orbiting around it but receiving less and less warmth as the millennia pass. The remnant star is still there, but the fire is out, and the planets, if they remain, are growing colder. There is something quietly moving about the white dwarf and its planets. Astronomers have found white dwarfs with evidence of planetary material in their atmospheres. The white dwarf, in its cooling, sometimes draws in rocky material from the remnants of its planetary system, and the chemical signatures of that material appear in the white dwarf spectrum. Calcium, magnesium, silicon, iron, the minerals of rocky worlds absorbed into the stellar remnant. A star consuming, in its old age, the remnants of the worlds it once warmed. In some cases, whole planets continue to orbit white dwarfs, changed by the star's evolution, perhaps stripped of their atmospheres, perhaps reshaped by the intense radiation of the white dwarf's hot youth. But still there, still orbiting, worlds persisting around the cooling remnant of their sun, in a system growing ever darker and ever colder as the white dwarf slowly dims. That is a form of loyalty that the universe did not design, but that physics has created nonetheless. Worlds that stay, even after the fire goes out, orbiting their cooling remnant sun in patient, unchanging circles for billions and eventually trillions of years. Let that image rest with you. The white dwarf, slowly cooling and its world still circling, patient, persistent, gradually darkening. Part of the universe's immense, quiet, slowly fading population of remnants and forgotten things. We left off with the white dwarf and its patient, cooling existence, its world still circling in the growing dark. But there is more to say about white dwarfs, because they are not simply the passive recipients of a fate that was assigned to them. They are objects with their own complex chemistry, their own internal physics, their own ways of interacting with whatever remains around them. And in their long, cooling lives, they do things that are genuinely extraordinary. One of the most remarkable things about white dwarfs is what happens to their interiors as they cool. A white dwarf is made primarily of carbon and oxygen, the products of the nuclear burning that occurred during the star's active life. For a long time, the interior of a white dwarf is hot enough that these elements remain in a gaseous or liquid state, swirling in a dense plasma. But as the white dwarf cools toward lower and lower temperatures, something extraordinary is predicted to occur in the core. The carbon and oxygen begin to crystallize. The interior of a cooling white dwarf is expected to solidify from the center outward, forming a crystal structure, an enormous diamond-like lattice of carbon and oxygen nuclei arranged in a regular pattern. An object roughly the size of the Earth, made of crystallized carbon and oxygen, cooling slowly in space. A diamond star, not metaphorically, but in a very genuine physical sense. Astronomers found the first observational evidence for this crystallization process in 2019, detecting a pileup of white dwarfs at certain temperatures and luminosities in data from the Gaia spacecraft. The pattern matched the predictions for what would happen if white dwarfs were releasing extra energy as their interiors crystallized, effectively slowing their cooling at that stage. The evidence suggested that the crystallization of white dwarf interiors is not just a theoretical prediction, but a real physical process happening in billions of white dwarfs across the galaxy right now. Right now, in the galaxy, there are billions of slowly cooling spheres of compressed carbon and oxygen, their interiors gradually crystallizing from the center outward, releasing a small additional pulse of energy as the crystal lattice forms, then resuming their long cooling. Enormous cosmic gems drifting in the dark, invisible to the naked eye, slowly becoming something that the universe's chemistry has never produced through any other process. There is also what happens when a white dwarf is not alone. Many stars form in pairs, two stars orbiting each other, living out their stellar lives in each other's company. When one of them evolves and eventually becomes a white dwarf, the pair continues. The white dwarf orbits its companion, and if the companion is close enough, the white dwarf's gravity can begin to pull material from the companion's outer layers. The companion's gas streams across the space between them and falls onto the white dwarf, accumulating on its surface. This process can lead to two very different outcomes, depending on how quickly the material accumulates. If it accumulates slowly, the hydrogen on the surface of the white dwarf can periodically ignite in a thermonuclear flash, a nova, a sudden brightening as the accumulated layer ignites and burns off. These novae recur every few years or decades or centuries, a white dwarf periodically flaring into temporary brightness as it burns off the material its companion is providing. A failed star, briefly pretending to be a real one. If the material accumulates quickly, or if the white dwarf is already near the maximum mass that electron degeneracy pressure can support, the accumulation can push the white dwarf over that limit. The electron degeneracy pressure suddenly fails. The white dwarf can no longer support itself, and it collapses and explodes in a Type Ia supernova, one of the most energetic events in the universe. A white dwarf, that patient cooling remnant, achieving in its death a brightness that can briefly outshine its entire host galaxy. But most white dwarfs have no companion. Most white dwarfs drift alone, cooling quietly, crystallizing slowly, darkening gradually over time scales that dwarf the current age of the universe. They are the patient majority, the quiet remnants of the majority of all stars that have ever lived and died. Billions of them in the Milky Way alone, each one a former sun, each one preserving within its compressed interior the chemical record of the nuclear burning that occurred during its active life. Each one on its long, slow journey toward a final darkness that the universe has not yet had time to reach. And when they finally go dark, when the last of their heat is radiated away and the last photon escapes from their crystallized interiors, they will become black dwarfs. Cold, dark, perfectly preserved spheres of crystallized carbon and oxygen. The most permanent objects in the universe in a sense, not destroyed, not dissolved, simply cold, simply dark. Simply there in the void. For as long as the universe continues to exist, the black dwarf is the ultimate forgotten object. Not forgotten because it was never interesting, not forgotten because it formed without drama or purpose. Forgotten because it completed its entire life cycle, because it went from gas cloud to star to white dwarf to black dwarf, through billions of years of burning and billions more of cooling, and arrived finally at a state of perfect, permanent invisibility. Not dead in the dramatic sense, not destroyed, simply finished, and still there. The universe does not clean up after itself. The black dwarfs, when they eventually form, will persist for an almost incomprehensible length of time. They will be there when the last stars burn out. They will be there when the galaxies disperse. They will be there, cold and dark and crystalline, drifting through a universe so old and so dark that the very concept of visibility has ceased to have meaning. And they will carry within them in their crystal lattices the memory of the hydrogen that once burned in their cores, the memory of the helium that formed from it, the memory of the carbon and oxygen that was made from the helium. A perfect chemical archive of a stellar life, preserved in diamond in the dark. Breathe with that thought for a moment. The universe keeps its memories in unexpected ways, not always in light, sometimes in crystal. Sometimes in the quiet, cooling permanence of things that have finished their burning and simply persisted. We have now visited 6 categories of forgotten objects. The brown dwarfs, cooling slowly in numbers comparable to the stars themselves. The rogue planets, wandering in the dark between the stars in numbers that may exceed the stars. The orphaned moons, fragments of former systems drifting as archives of lost solar histories. The dark galaxies, galaxy-scale structures that never lit up, or that are slowly going dark, invisible within the clusters they inhabit. The intergalactic stars, burning faithfully in the voids between galaxies, their light traveling for millions of years before reaching anything. And the failed stellar remnants, the white dwarfs cooling toward an eventual perfect darkness, the neutron stars spinning in isolation, the products of stellar endings drifting quietly through the galaxy. Now let us try to hold all of this together. Let us attempt, as gently as we can, to take a census, to ask not just what these objects are individually, but what their combined presence means for our picture of the universe as a whole. What fraction of everything is bright? What fraction is quiet? When we add up all the forgotten, all the dim, all the dark, all the drifting, what do we find? The answer is one of the most striking facts in all of modern cosmology. And it comes in several layers, each one more profound than the last. The first layer is the ordinary matter layer, the layer that includes everything we have been talking about tonight. All the stars, all the brown dwarfs, all the rogue planets, all the remnants, all the gas, all the dust, all the rocks and ice and metals that make up all the material objects in the universe. Everything that is made of protons and neutrons and electrons. Everything that is, in the technical language of physics, baryonic matter. All of it, the blazing and the forgotten alike, added together. How much of the universe's total mass energy does all of this ordinary matter represent? About 5%. 5%. All the stars, all the brown dwarfs, all the rogue planets, all the moons and asteroids and comets and white dwarfs and neutron stars and black holes and gas clouds and dark galaxies and intergalactic stars. All the ordinary matter, bright and dim and dark combined, is only about 5% of what the universe contains. The remaining 95% is divided between two things whose natures we do not yet fully understand. About 27% is dark matter, the invisible substance that holds galaxies together, that forms the scaffolding of the cosmic web, that provides the majority of the mass in most galaxy clusters. We know dark matter exists because of its gravitational effects. We have mapped it, in a sense, through those effects, but we do not know what it is made of. We have not directly detected a dark matter particle. It is real, it is everywhere, it constitutes more than a quarter of the universe's total mass energy, and we do not know what it is. The remaining 68% of the universe's mass energy is something called dark energy. Dark energy is what drives the accelerating expansion of the universe. It is a property of space itself, or something that behaves like a property of space, pushing the fabric of the universe outward faster and faster with every passing eon. Like dark matter, we know dark energy exists because of its effects. Unlike dark matter, we do not even have good candidate particles or fields to explain it. It is a name for our ignorance, a placeholder for something fundamental that we have not yet understood. So the universe is 5% ordinary matter, 27% dark matter, and 68% dark energy. The visible ordinary matter, the stars that we see when we look up at the night sky, represents only a small fraction of even that 5%. Most of the ordinary matter in the universe is not in stars. It is in gas, dispersed across the cosmic web, in the intergalactic medium, in halos around galaxies, in forms that are difficult to observe and easy to overlook. The bright stars constitute perhaps half of 1% of the total mass energy of the universe. Half of 1%. That is what the night sky shows us. Half of 1% of what is actually there. All the mythology, all the navigation, all the poetry, all the science that humanity has built around the visible stars around those points of light that have defined our relationship with the cosmos for our entire history as a species. All of that is built around half of 1% of what exists. Now, it would be a mistake to conclude from this that the night sky is somehow an illusion, or that the stars are unimportant, or that the 5% of ordinary matter is less real or less significant than the dark matter and dark energy that dwarf it. The stars are real. Their light is genuine. Their nuclear fires are among the most important processes in the universe for creating the chemical elements that make planets and life possible. The significance of something is not determined by its abundance. But the proportion is still humbling, and it invites us to think carefully about what we mean when we say we understand the universe. We have built our models, our theories, our cosmologies, our stories, around what we can see. And what we can see is a tiny fraction of what there is. The universe that we have named and mapped and celebrated and feared is a thin, visible layer on top of something vastly larger and almost entirely unknown. Even within that thin, visible layer, as we have discovered tonight, much of the ordinary matter is not in the bright stars but in the forgotten objects, in the brown dwarfs outnumbering the stars, in the rogue planets outnumbering both, in the white dwarfs slowly cooling, in the intergalactic stars shining for no one, in the dark galaxies drifting unseen in the clusters. The visible is already a minority within the visible. This layered picture of invisibility, of majority hidden within majority, is perhaps the most important thing we can take from tonight's journey. The universe is not primarily what we see. It is primarily what we do not see. The dark and the quiet and the dim and the forgotten outnumber the bright and the dramatic and the visible at every scale, from the scale of individual stellar objects to the scale of the universe itself. And somehow, knowing this is not disorienting. It is, strangely, steadying. It means the universe is larger and more varied and more abundant than any picture we have ever drawn of it. It means the familiar stars are surrounded by an unseen abundance. It means the cosmos is fuller than it looks, not emptier, fuller. Rest with that thought as your breathing slows. The universe is full, mostly quiet, mostly dark, mostly drifting, but full. There is a philosophical shift that happens when you truly absorb the numbers we have been discussing tonight. When you understand that brown dwarfs are at least as numerous as stars. When you accept that rogue planets may outnumber everything. When you see that dark matter constitutes 5 times as much mass as all the ordinary matter in the universe combined, and that dark energy dwarfs even that. When all of this settles into the mind, not just as a collection of statistics, but as a description of what reality actually is, a shift occurs. The shift is this. You stop thinking of the spectacular as typical. You stop assuming that the cosmos is primarily a place of blazing stars and dramatic collisions and violent energy. You begin to see that the universe's default condition, its most common state, its characteristic mode of being, is not the spectacular. It is the subtle. The universe prefers subtlety, not as a conscious choice, not as an aesthetic preference, but as a simple matter of how physics distributes matter and energy and objects across the range of possibilities. The dramatic and the brilliant are real, but they are the exception. The cold and the dim and the slowly cooling are the rule. Think about what this means in practical terms. A brown dwarf, one of those cold, dim, slowly fading almost stars, will outlast any true star by an almost unimaginable margin. The most massive stars, the brilliant blue supergiants that blaze at the top of the stellar hierarchy, live for only a few million years. They are born, they burn furiously, they explode in spectacular supernovae, and they are gone in what amounts to a geological eye blink on cosmic time scales. Our own sun, a much more modest and ordinary star, will live for about 10 billion years. But a red dwarf star, the smallest and dimmest of the true stars, can burn for 100 billion or even a trillion years. A brown dwarf, that failed ignition, that cooling ember, will persist for even longer than that, cooling so slowly that in any practical sense it persists forever. So in terms of duration, in terms of how long an object exists and carries on, the dim objects win. The spectacular is brief. The subtle is eternal. This is not a new philosophical observation. Humans have been drawn to the bright and the dramatic in the sky for as long as we have looked upward, and we have always known at some level that the most dramatic events are the shortest lived. A shooting star is spectacular precisely because it lasts only a moment. A supernova is extraordinary precisely because it is rare and brief. The steady, unremarkable light of an ordinary star, burning for billions of years, produces far more total light over its lifetime than any dramatic outburst. The ordinary wins in the end, even in terms of total output. But the revelation of the forgotten objects goes further than this familiar observation. It is not just that ordinary things last longer. It is that ordinary things, and the things below ordinary, the things so dim and cold and dark that we barely count them, are so much more numerous that the spectacular is drowned in comparison. For every supernova that lights up a galaxy, there are billions of white dwarfs cooling quietly. For every blazing quasar illuminating the early universe, there are trillions of rogue planets drifting in the dark. The dramatic events are real, but they are tiny in number compared to the quiet majority. The universe, if we are being honest about what its census reveals, is primarily a collection of cold, dim, slowly changing things. Gas clouds drifting between stars, brown dwarfs cooling in the galactic disk, rogue planets wandering between the stars, white dwarfs radiating the last of their heat into the void, dark matter halos extending invisibly around galaxies, and dark energy suffusing all of space, pushing everything gradually outward, the most pervasive and the most invisible of all. Against this backdrop, a blazing star like our Sun is a remarkable exception, not the rule. An event that requires very specific conditions to occur, that is genuinely impressive when it happens, but that represents only a tiny fraction of the universe's total inventory. The Sun is wonderful, and we are immeasurably fortunate to orbit it, but it is not the universe's default condition. The default condition is cooler, dimmer, quieter, and more spread out than any star. This philosophical reorientation has a practical implication for how we do science. For most of human history, and for much of the history of astronomy, we have studied the universe by looking at what is bright. We have pointed our telescopes at stars, at galaxies, at clusters, at the most luminous things we could find. And we have learned an enormous amount from this approach. The universe has revealed its laws of physics, its chemical compositions, its age and its structure, through the light of the things we can see. But the forgotten objects are teaching us that this approach, however productive, is incomplete. If most of the universe's ordinary matter is not in stars but in gas and dim objects and remnants, then a science that focuses exclusively on the bright will systematically miss the majority. The surveys that found brown dwarfs in large numbers, the microlensing programs that revealed the population of rogue planets, the deep imaging techniques that uncovered the ultra-diffuse and dark galaxies, all of these represent a different approach. An approach that looks not for the brightest thing in a region of sky, but for the faintest. Not for the most dramatic signal, but for the most subtle. The universe rewards subtlety in scientific approach as well as in physical character. The quietest objects have the most to teach about the full nature of the cosmos, precisely because they constitute the most of it. There is a kind of wisdom in this, not the wisdom of mysticism or of metaphor, but the wisdom of honest accounting. The universe is telling us, through the distribution of its objects, that most of existence does not announce itself. Most of reality is not trying to be noticed. It is simply there, doing what physics requires it to do, at the temperature and brightness and scale that physics has assigned it, without any particular interest in whether we are paying attention. And the appropriate response, if we want to understand reality rather than only the most convenient or impressive part of it, is to learn to pay attention to the quiet as well as the loud, to develop instruments sensitive enough to find the dim things, to build theories that account for the invisible as well as the visible, to ask not just what is brightest in this region of space, but what is most numerous, not just what is most dramatic, but what is most typical. The universe prefers subtlety, and science at its best is learning to match that preference, learning to see what the universe is actually like, rather than only what is easiest to see. That is a lesson worth sitting with as the night deepens and the mind quiets. The most real things are not always the most obvious ones. The universe's quiet majority drifts on regardless of our attention. And in that independence, that quiet persistence, there is something genuinely beautiful. The idea of quiet abundance, of a universe that produces far more of the overlooked than the spectacular, is not just a fact about distant objects in space. It is a frame that can be placed over many different aspects of existence, and when it is, it tends to shift things in an interesting direction. Tonight, as we approach the final part of our journey together, I would like to sit with that frame for a while, not to draw grand conclusions or make sweeping philosophical pronouncements, but to let the image of the quiet majority settle gently into the mind and see what it illuminates. We are a species that evolved to notice the dramatic. Our ancestors needed to notice the predator that moved suddenly, the storm that gathered on the horizon, the rival group approaching across the savannah. The subtle and the slow and the persistent could often be taken for granted, while the sudden and the bright demanded immediate attention. This is not a flaw, it is an adaptation. But it means that our default attention settings are calibrated for a world of dramatic events, and we have to work, consciously and deliberately, to notice the quiet abundance that surrounds us at every scale. Think about the world you inhabit on an ordinary day. The most noticeable things are the dramatic ones. The argument, the accident, the unexpected news, the sudden joy. But the majority of any given day is not made of those things. It is made of quieter things. The way light falls through a window in the morning, the particular feeling of a familiar chair, the background rhythm of a city or a countryside that you have learned to hear as silence because it is so constant. The presence of other people going about their lives in the same space you are in. These quiet things are more numerous than the dramatic ones. They constitute more of the texture of a life. But they are easy to overlook, easy to pass through without noticing, because they do not announce themselves. The forgotten objects of the universe are doing the same thing. The brown dwarfs do not announce themselves. The rogue planets do not wave. The orphaned moons carry their chemical archives in perfect silence. They are the background radiation of the universe's object population, the quiet majority that constitutes more of the total than the stars that have always drawn our eyes. And just as learning to notice the quiet things in a daily life tends to make that life feel richer and fuller, learning to notice the quiet majority of the cosmos tends to make the cosmos feel richer and fuller too. Not emptier because most of it is dark. Fuller because the darkness is not empty, it is populated. The space between the stars is not nothing. It is full of brown dwarfs and rogue planets and orphaned moons and cooling white dwarfs and the invisible haze of dark matter. The space between galaxies is not nothing. It is full of intergalactic stars and diffuse gas and the gravitational whispers of structures we have only recently learned to detect. When you look up at the night sky and see the stars, you are seeing a small fraction of what is actually there. But that fraction is real. The stars are genuinely there, and all around them in the spaces between and beyond is the rest. The forgotten majority, real, persistent, quietly abundant. There is also something in the forgotten objects that speaks to the question of what it means to have value. We tend to measure value by visibility, by brightness, by impact, by the size of the impression something makes on the world around it. A supernova is valuable because it is dramatic. A quasar is significant because it is so luminous. We tend to think of the universe's most energetic events as its most important ones. But the forgotten objects suggest a different kind of value. The white dwarf that cools for trillions of years is not doing something dramatic, but it is preserving something. It is carrying within its crystallizing interior the chemical record of a stellar life, the elements produced by billions of years of nuclear burning, elements that may eventually, in some distant future epoch of the universe, be incorporated into new structures, new bodies, new processes. The patient persistence of the white dwarf is not glamorous, but it is real, and it is productive in ways that take an incomprehensibly long time to unfold. The rogue planet drifting through interstellar space is not doing anything obvious, but it is carrying its geology, its chemical complexity, its potential for hosting liquid water and the processes associated with it. It is a repository of materials and conditions that may, over billions of years, find their way into new contexts. The universe does not waste its material. It distributes it, stores it in the quiet objects, and lets time and gravity and chemistry find new arrangements. The quiet abundance is not passive. It is patient, and patience at cosmic time scales is indistinguishable from productivity. This is perhaps the deepest thing the forgotten objects can teach us, that the universe's most numerous and most persistent objects are not the flashy ones, that the work of the cosmos is not primarily done in supernovae and quasars and galaxy collisions, although those events matter. The work is done in the slow cooling of a billion white dwarfs, in the long drift of a rogue planet through the spaces between stars, in the gradual crystallization of a brown dwarf's iron clouds, in the patient accumulation of gas in a dark galaxy's slowly evolving halo. The dramatic events are the punctuation. The quiet objects are the sentences. And the sentences carry more meaning than any exclamation mark. As you rest here tonight in the quiet of wherever you are, consider that you are part of the same universe that contains all these patient, forgotten, quietly abundant things. Your body is made of atoms forged in stars and scattered by supernovae, yes, but those atoms have spent the vast majority of their existence in quiet states. In rocks, in oceans, in clouds, in the bodies of organisms that lived and died long before you. The dramatic moments of their history, the supernovae that created them, the collisions that distributed them, are a tiny fraction of the total time they have existed. Most of the time, atoms are simply there, in whatever configuration they happen to occupy, doing what chemistry and physics require them to do without drama or announcement. You, reading this or listening to this in the quiet of your night, are a temporary and extraordinary configuration of patient atoms. And the universe around you, far beyond what the night sky reveals, is full of other patient things, drifting, cooling, crystallizing, wandering. The quiet abundance of existence of which you are one small, brief, conscious part. Let that be a comfort. You do not need to be dramatic to be real. The universe has been demonstrating that principle on the largest possible scales since before the first star ignited. The quiet things are the majority, and the majority, in the end, is what the universe actually is. There is also a more intimate version of this lesson. Think about the people in your life who are quiet. Not the ones who announce themselves, not the ones who dominate every conversation, not the ones whose presence is immediately dramatic and visible. Think about the quiet ones, the ones who listen more than they speak, the ones whose contributions are steady and reliable rather than sudden and spectacular, the ones who are easy to overlook in a crowd but whose absence, when it occurs, leaves a gap that takes a long time to recognize and an even longer time to fill. The universe's quiet majority, in some ways, resembles these quiet people, not demanding attention, not announcing their importance, simply present, simply persistent, simply doing the patient work that the cosmos requires of them. And just as learning to notice the quiet people in your life tends to enrich that life considerably, learning to notice the quiet objects of the universe tends to enrich the picture of the cosmos considerably. Not because the bright and dramatic things are unimportant, but because they are incomplete without the quiet majority that surrounds them. The night sky that we love and have always loved, with its bright stars and its occasional planets and its rare dramatic events, is like a conversation that has been dominated by a few loud voices. Beautiful, interesting, worthy of attention, but not the whole conversation. The rest of the conversation, the quiet parts, the patient parts, the parts that have been going on in the background for billions of years without anyone paying close attention, is just as real and just as valuable. It is simply harder to hear. And learning to hear it, whether in a life or in a cosmos, is one of the quieter and more enduring forms of wonder. We are near the end of our journey tonight, and as we approach the end, I want to do something a little different. I do not want to summarize. I do not want to give you a list of things to remember, a recap of the objects we have visited. You have already met them. The brown dwarfs and their iron clouds, the rogue planets drifting in the dark, the orphaned moons carrying their chemical histories, the dark galaxies vast and ghostly, the intergalactic stars burning for no one, the white dwarfs crystallizing slowly toward an eventual perfect darkness. You know them now, at least a little. And what I would like to do instead of summarizing is to simply rest with them for a while. Imagine the galaxy as it truly is, not as it appears in our textbook illustrations or our popular science images, those bright, beautiful photographs of spiral arms lit up with the blue light of young stars and the red glow of nebulae. Imagine it more honestly. Imagine the full population. For every bright star visible in those images, imagine several brown dwarfs in the surrounding space, invisible, radiating their faint warmth into the dark. For every planetary system neatly arranged around its star, imagine the rogue planets drifting through the gaps between stars, alone and cold and real. For every moon shown orbiting a planet in a diagram, imagine the orphaned ones, the former companions that lost their planets and now drift as solitary bodies through interstellar space. For every galaxy captured in a deep field image, imagine the dark ones sitting unseen alongside them, vast and diffuse and almost entirely dark. And threading through all of it in the spaces between the galaxies, imagine the intergalactic stars, burning faithfully in voids so large that their light takes millions of years to reach the nearest galactic shore. And then, underneath all of this ordinary matter, bright and dim and dark alike. Imagine the dark matter. Invisible, pervasive, 5 times more massive than all the ordinary matter combined, forming the scaffolding on which everything else is arranged. The halos around galaxies, the filaments threading through the cosmic web, the hidden foundation of all visible structure, and permeating all of space, not a thing exactly, but a property of space itself. Imagine the dark energy, quietly, inexorably pushing everything apart, expanding the universe at an accelerating rate. The most abundant component of the cosmos and the most mysterious and the most invisible. This is the universe as it actually is, not primarily a collection of blazing stars, although the stars are real and important. Not primarily a collection of bright galaxies, although the galaxies are real and remarkable. Primarily a vast, mostly dark, mostly quiet, mostly invisible, mostly drifting collection of things that do not announce themselves. The universe is, in the most literal and quantitative sense, almost entirely made of things we cannot see, and we exist within it. On a small rocky planet, orbiting an ordinary star, in the middle zone of a spiral arm of a typical galaxy, within a modest cluster of galaxies, on the edge of a supercluster, in one filament of the cosmic web, inside the observable universe, surrounded on all sides by the quiet majority that our naked eyes cannot see. Brown dwarfs perhaps closer to us than the stars we know by name. Rogue planets crossing the galaxy on orbits that carry them through the same regions our solar system traverses over millions of years. White dwarfs scattered throughout the galactic disk like cooling embers, and dark matter surrounding everything, the invisible ocean in which the visible islands float. This is not a lonely picture. It might feel lonely at first, the idea that most of the universe is invisible, that the familiar stars are a thin, bright layer on top of an enormous, invisible substrate. But there is another way to feel it. We are surrounded. We are embedded in a cosmos so full of things, so populated at every scale, that the space around us, which looks dark and empty to our eyes, is actually teeming with objects and processes and ancient history. The night sky is not a window onto emptiness. It is a window onto the smallest visible fraction of a cosmos that extends, in its full complexity and abundance, far beyond what any light can show. And we can know this, not by seeing it with our naked eyes, but by thinking, by building instruments, by developing the mathematics that describes how objects form and evolve, by carrying out the surveys and the simulations and the careful measurements that reveal what is hidden, by asking not just what is brightest, but what is most numerous, by learning to find the subtle alongside the spectacular. The forgotten objects of the universe are not truly forgotten, not anymore. They were forgotten for most of human history, invisible and uncounted. But science has begun the work of remembering them. The infrared telescopes that find brown dwarfs, the microlensing surveys that reveal rogue planets, the low-surface brightness imaging that uncovers dark galaxies, the careful photometry of galaxy clusters that maps the intracluster light, the gravitational measurements that reveal dark matter, the supernova observations that expose dark energy. Each of these is an act of remembering, a deliberate effort to include in our picture of the universe the things that do not include themselves. And as we remember more of them, as our picture becomes more complete, the universe does not shrink. It grows. It becomes richer and more populated and more varied than the star-focused picture we began with. The more we learn to see the forgotten, the more the universe reveals itself to be an extraordinary place, not just in the obvious way of blazing stars and violent collisions, but in the deeper way of quiet abundance, of patient persistence, of an almost incomprehensible variety of objects existing at almost every scale. Tonight you have rested with some of the forgotten. You have let their existence settle into your awareness. The brown dwarfs drifting in the spaces near our solar system. The rogue planets crossing the galaxy in their long, sunless arcs. The orphaned moons carrying their frozen archives. The dark galaxies sitting unseen in their clusters. The intergalactic stars burning in the voids. The white dwarfs cooling toward their eventual crystal darkness. They do not need your awareness. They will continue regardless. The universe's quiet majority does not require an audience. But giving them your attention, even briefly, even from the warmth of wherever you are resting tonight, is a small act of honest reckoning with what the cosmos actually is. An honest reckoning with what is real has a way of making the mind quiet and the body relaxed, and the sense of one's own place in the universe more settled and more at peace. The forgotten objects drift in the dark, patient, ancient, real. And you, in your small and brief and conscious way, have noticed them tonight. That is enough. Rest now. And so we arrive at the end of tonight's wandering. We began in the familiar night sky, among the stars that human beings have always seen, and we moved gradually into the spaces where the forgotten things drift. We met the objects that outnumber the stars and the objects that exist between and beyond them. We sat with the dark and the dim and the slowly cooling and the quietly abundant. And now, as all good journeys do, this one comes to a gentle resting place. The night around you, wherever you are, is full of a particular kind of quiet. It is the quiet of a mind that has traveled through large ideas and is ready to settle. It is the quiet that comes after thinking about scales that exceed the human, after sitting with numbers too large to hold, after letting the imagination stretch as far as it will go, and then releasing it to return to the familiar and the immediate. You are here, in a body on a planet under a sky. Whether the sky is clear or cloudy, whether you can see stars or only the glow of a city, whether it is truly night or merely the night of a closed room, you are on a small world orbiting a star that is part of a galaxy that is part of a cluster that is part of a supercluster. All of it surrounded by the invisible majority of dark matter and dark energy, and quiet drifting things that constitute the true nature of the cosmos. You are, in your way, one of the quiet things, one of the ordinary things that the universe produces without drama. Your body is made of elements that were forged in stellar interiors and scattered by ancient supernovae. Your consciousness is a brief and remarkable process that the universe has somehow arranged in this particular configuration of matter. And tonight, in this quiet moment, that consciousness has reached out and touched something of the universe's hidden majority, has given a moment of attention to the forgotten, has acknowledged the brown dwarfs and the rogue worlds and the dark galaxies and the lonely stars in the void. It is a small thing, but it is the kind of small thing that matters. The universe does not notice being noticed, but we are changed in small ways by noticing it, by allowing its actual nature to settle into our understanding, by expanding our sense of what exists to include the quiet as well as the spectacular. As your eyes grow heavier as the journey through large ideas fades into the softer textures of sleep, let the image of the forgotten objects remain for a moment, not as something to worry about or analyze, simply as a kind of company. The brown dwarfs drifting close, the rogue planets crossing the galaxy on their long arcs, the orphaned moons carrying their frozen histories through interstellar space, the dark galaxies, vast and ghostly in their clusters, the intergalactic stars burning faithfully in the void, the white dwarfs cooling slowly, crystallizing, persisting, all of them real, all of them there, all of them part of the same universe that contains this moment, this room, this breath. The cosmos is mostly subtle, and in its subtlety it is more than the eye can see, more than the mind can fully hold, more than any one journey can entirely describe. But we come back. We make the journey again, each time a little further, each time with a little more willingness to look into the dimmer corners, to ask what is there that is not announcing itself, to practice the kind of attention that the universe's quiet majority deserves. If this journey brought you something, a moment of calm, a new way of seeing the night sky, a comfortable perspective on the scale of things, then it has done what it set out to do. And if you find yourself curious, if you want to know more about the brown dwarfs or the rogue planets or the dark galaxies or the crystal interiors of cooling white dwarfs, the science is there waiting for you, patient and abundant, the way the objects themselves are patient and abundant. For now, though, the only thing to do is rest. Let the body grow heavy. Let the thoughts slow. Let the forgotten objects drift where they drift. They will be there tomorrow and the day after and for billions of years beyond. They do not need your wakefulness to continue existing. They are fine. They are persistent. They are the quiet majority of a cosmos that is older and larger and darker and more wonderful than it has ever needed to be. And you are part of it, resting in it, cared for by a small star on a small world in the middle distance of a spiral arm, surrounded by the invisible abundance of everything that the night does not show. Good night. Sleep well. The forgotten objects drift on. Before we reached the white dwarfs in our inventory of stellar remnants, we mentioned in passing another kind of remnant, one that forms when a more massive star ends its life. When a star with between roughly 8 and 20 times the mass of our sun exhausts its nuclear fuel and its core collapses, the result is not a white dwarf. It is something far more extreme. The core collapses so quickly and so completely that the electrons and protons of the stellar material are crushed together, combined by the enormous pressure into neutrons. The result is an object called a neutron star. And neutron stars, for all their extraordinary nature, are among the most overlooked and most poorly appreciated of the universe's quiet objects. A neutron star is almost incomprehensible in its density. A typical neutron star contains roughly 1.5 times the mass of our sun, compressed into a sphere about 20 kilometers across. 20 kilometers, the mass of a star, packed into something roughly the size of a city. A teaspoon of neutron star material would weigh billions of tons on Earth. The gravity at the surface of a neutron star is about 200 billion times the gravity at the surface of Earth. If you could somehow stand on the surface of a neutron star, the gravity would compress you to a layer thinner than an atom in a fraction of a second. The interior of a neutron star is a place where physics reaches conditions that no laboratory on Earth can replicate. The neutrons themselves, packed together at densities exceeding those found in the nucleus of an atom, behave in ways that our understanding of physics cannot fully describe. There may be exotic states of matter in the deep interiors of neutron stars, forms of matter that exist nowhere else in the observable universe. Some theoretical models suggest that at the very center of the most massive neutron stars, the density becomes so extreme that individual neutrons dissolve into their component quarks, forming a state called quark matter. Whether this actually occurs is one of the open questions of modern physics, and neutron stars are the only naturally occurring laboratory in which it could possibly be tested. But neutron stars are also, in their way, quiet objects. They are not visible to the naked eye. They do not shine invisible light the way ordinary stars do. Many neutron stars are detected only because they are spinning rapidly and emitting beams of radio waves that sweep across the sky like cosmic lighthouses. These are called pulsars, and the regularity of their pulses is so precise that they have been used as cosmic clocks, their timing accurate enough to test the predictions of general relativity with extraordinary precision. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University. The signal was so regular, pulsing with a period of about 1 1/3 seconds, that it was initially taken seriously as a possible signal from an extraterrestrial intelligence. The researchers privately nicknamed the source LGM-1 for Little Green Men. It turned out to be a rotating neutron star, the remnant of a stellar explosion, spinning at a remarkable rate and sweeping its beam of radio waves across the Earth with clock-like precision. The universe had produced something so regular and so apparently deliberate that the first humans to detect it thought it might be a message. But the vast majority of neutron stars are not oriented such that their beams sweep across the Earth. They spin in the dark, beaming their radio waves across the galaxy, but those beams never cross our detectors. They are invisible to us. We detect perhaps a few thousand pulsars in the Milky Way. The estimated total population of neutron stars in our galaxy is somewhere between 100 million and 1 billion. The fraction we can detect is tiny. The rest spin in the dark, invisible, cooling more slowly than white dwarfs due to their different internal physics, persisting for billions of years as dense, spinning, quiet remnants of the most violent stellar deaths the universe produces. Some neutron stars spin extraordinarily fast. The fastest known pulsars spin at over 700 times per second. At those rotation rates, the surface of the neutron star is moving at a significant fraction of the speed of light. The centrifugal forces at the equator are immense, distorting the already extreme object into a slightly oblate shape. These millisecond pulsars are thought to have been spun up by the accretion of material from a companion star, the angular momentum of the infalling material gradually increasing the neutron star's rotation rate until it reaches these extraordinary speeds. A neutron star, that quiet remnant, can be rejuvenated by a companion, spun up to dizzying rates, transformed from a slowly cooling object into a furiously spinning one. There are also neutron stars with extraordinarily intense magnetic fields. These are called magnetars, and they are among the most energetic objects in the universe during their active periods. A magnetar's magnetic field can be about 1,000 times stronger than that of an ordinary neutron star, itself already an immensely powerful magnet. The magnetic stresses in a magnetar can crack the star's solid crust, producing brief but enormously powerful bursts of X-rays and gamma rays. A magnetar flare can, for a fraction of a second, outshine the combined light of all the stars in the Milky Way. And yet magnetars are, between their outbursts, quiet objects. They cool. They spin down. Their magnetic fields gradually decay, and over millions of years they fade into the general population of old, cold, slowly fading neutron stars. The neutron star population of the Milky Way represents a kind of geological record of the galaxy's star formation history. Every neutron star was once a massive star, and massive stars are short-lived, burning their fuel in millions rather than billions of years. The distribution of neutron stars in the galaxy reflects the pattern of massive star formation over the galaxy's history. The spiral arms where stars are born, the regions of past vigorous star formation, the ancient stellar populations of the galactic bulge and halo. In this sense, the quiet neutron stars drifting through the galaxy are a fossil record, an archive of the galaxy's past written in the distribution of dense, spinning, cooling remnants. And like all the forgotten objects, they are there in enormous numbers. 100 million to 1 billion neutron stars in the Milky Way alone, each one the remnant of a stellar death that was, briefly, one of the most violent events in the galaxy. Each one now cooling, spinning, drifting, carrying within its dense interior the extreme physics of matter under conditions that exist nowhere else. Each one invisible to the naked eye, detectable only to the most specialized instruments, part of the galaxy's quiet majority of forgotten things. The neutron star is perhaps the most extreme of the forgotten objects. In its brief violent birth, it announces itself with a supernova bright enough to be seen across a galaxy. But then it settles. The violence passes, and what remains is a small, dense, spinning thing in the dark, doing the quiet work of cooling and drifting and carrying its physics through the galaxy for billions of years. The most dramatic possible birth, followed by one of the quietest possible existences. That transition from the spectacular to the subtle is in a sense the whole story of the forgotten objects. They begin in drama, or they are formed in drama, or they are defined by a dramatic absence of what was expected. And then they persist, quietly, patiently in the dark, for a very long time. Let the image of the neutron star rest with you for a moment. Something the size of a city, spinning hundreds of times per second, containing the density of an atomic nucleus, drifting through the galaxy in perfect invisible silence. One of a billion in the Milky Way alone. Forgotten because the drama of its birth has long since faded, and what remains is too small and too dim and too extraordinary to easily see. There is one more aspect of neutron stars worth mentioning before we leave them. They can merge. When two neutron stars orbit each other in a binary system, they lose energy gradually through the emission of gravitational waves, the ripples in spacetime that Einstein's general relativity predicts, and that the LIGO gravitational wave detectors confirmed in 2015. As the neutron stars lose energy, their orbit shrinks. Slowly at first, then faster, then very fast, the two dense objects spiral toward each other, and then they collide. The collision of two neutron stars is one of the most energetic events in the universe. It produces a kilonova, a burst of light and heat and gravitational waves and a spray of exotic heavy elements. Gold, platinum, uranium, the heaviest elements in the periodic table, are thought to be produced primarily in these neutron star mergers. The gold in any jewelry you own, the platinum in any catalytic converter, was almost certainly made in the collision of two neutron stars, somewhere in the galaxy, billions of years ago. So the neutron star, that quiet, dense, forgotten remnant, is also the forge in which the heaviest elements are made. The most patient of objects, drifting in the dark for billions of years, occasionally brought into violent contact with a companion, producing in that final collision a legacy of heavy elements that will eventually find their way into new stars, new planets, new chemistry, new life. The patience ends in a moment of extraordinary productivity. The quiet object becomes, in its final act, a factory for the rarest and most useful elements in the universe. That transformation from quiet remnant to elemental forge is perhaps the most complete expression of the theme of the forgotten objects. They persist without drama. They cool and drift and spin and crystallize in the dark. And then, sometimes at the end or in a rare encounter, they produce something that the universe needs and cannot make any other way. The forgotten objects are not simply passive leftovers. They are, in the fullness of time, among the universe's most productive citizens. There is one more category of forgotten matter that we have not yet visited properly, and it may be the most overlooked of all, not because it is rare, but because it is so common, so pervasive, so much the background of the universe that it tends to disappear into the assumption of emptiness. I am talking about the gas. The cold, thin, dispersed gas that fills the spaces between stars within a galaxy, that connects the visible islands of bright nebulae and star clusters with a medium so thin it would be considered a near-perfect vacuum by the standards of any laboratory on Earth. And yet that is, in total, one of the most massive components of the galaxy. The interstellar medium, as astronomers call it, is not one thing but several. It exists in different phases, at different temperatures and densities, shaped by the processes of stellar birth and death that constantly stir and heat and cool and compress it. There is hot gas, heated to millions of degrees by supernova explosions, filling enormous bubbles in the galactic disk. There is warm gas, at tens of thousands of degrees, the medium in which clouds of cooler gas are embedded. There is cool neutral gas, at hundreds of degrees, filling large clouds that drift through the galactic disk. And there is the cold molecular gas, at just 10 to 30 degrees above absolute zero, gathered into the giant molecular clouds that are the direct precursors of new stars. All of these phases are part of the interstellar medium, and all of them are, in different ways, forgotten. The hot gas is invisible in optical light and is only detectable in X-rays. The warm gas emits visible light in some regions, where it is illuminated by nearby hot stars, but most of it glows only in wavelengths that our eyes cannot detect. The neutral gas is best detected through its radio emission, at a wavelength of 21 centimeters. The molecular gas is detected through the radio emission of molecules like carbon monoxide, or through the infrared glow of dust particles mixed with it. In each case, specialized instruments tuned to specific wavelengths are required to see what is there. And what is there is an enormous amount of mass. Estimates of the total mass of gas in the Milky Way vary, but a common figure is that the interstellar medium contains roughly 10% of the total mass of all the stars in the galaxy. For every 10 stars, there is roughly 1 star's worth of gas floating between them. That is an enormous reservoir of material, an archive of the galaxy's chemical evolution, a store of raw material for future star and planet formation. But the interstellar medium is not just mass, it is chemistry. The cold molecular clouds in particular are extraordinary chemical environments. Despite the extreme cold and the thinness of the gas, a remarkable range of molecules forms in these clouds. Over 200 different molecular species have been detected in interstellar space, ranging from simple diatomic molecules like hydrogen and carbon monoxide to increasingly complex organic compounds. Amino acids, the building blocks of proteins, have been detected in meteorites that are thought to preserve interstellar chemistry. The precursors to the chemistry of life, it seems, form not only on planets but in the cold molecular clouds between stars, assembled by the slow collisions of atoms and molecules on the surfaces of dust grains over millions of years. The chemistry of the interstellar medium is one of the most remarkable and least publicly appreciated areas of modern astronomy. In the cold, thin gas between stars, at temperatures just above absolute zero, in conditions of near-perfect vacuum, molecules form and grow. Some of them reach extraordinary levels of complexity by the standards of what anyone would expect to find between stars. Polycyclic aromatic hydrocarbons, large organic molecules containing dozens of carbon atoms arranged in ring structures, are found throughout the interstellar medium. They are thought to be among the most abundant complex molecules in the universe, and they are made, not in the warm and comfortable conditions of a planetary surface, but in the cold, irradiated, near-vacuum environment of the space between stars. This is a profoundly important point. The chemistry of life, or at least the precursor chemistry, does not require a planet to get started. It happens in the interstellar medium. It happens in the cold molecular clouds. It happens in the diffuse gas between galaxies. The universe is manufacturing organic chemistry everywhere, in the most inhospitable conditions, without any planet or star providing the warmth or the liquid water that we think of as prerequisites. And then that chemistry is delivered to young planetary systems when those systems form within collapsing molecular clouds, inheriting the chemical richness that the cloud had accumulated over millions of years. The Earth did not begin its chemistry from scratch. It began with a head start, a legacy of complex organic molecules built in the interstellar medium over millions of years before the Sun or the Earth even existed. The cold gas between stars, the most overlooked of the forgotten objects, may have provided the chemical seeds from which life eventually grew. The interstellar medium also tells the story of the galaxy's past in another way. The chemical composition of the gas in different parts of the galaxy reflects the history of stellar evolution there. Stars form from the gas, burn their nuclear fuel, and then return material to the gas through stellar winds and supernova explosions. But they do not return the same material they started with. They return enriched material that has been processed by nuclear burning and now contains heavier elements that were not present in the original cloud. Carbon, oxygen, nitrogen, silicon, iron, all the elements beyond hydrogen and helium that make rocky planets and biological chemistry possible, were made in stars and returned to the interstellar medium. The gas between the stars is an accumulation of this stellar processing, a reservoir that has been stirred and enriched by billions of years of stellar births and deaths. Each generation of stars makes the gas a little richer in heavy elements. Each generation of planets forms from slightly more chemically complex raw material. The cold gas between the stars is not just material for future stars. It is a record of all the stars that have come before, and it drifts there between the visible stars in enormous quantities, carrying its chemical history, manufacturing its organic molecules, hosting the processes that will eventually collapse into new stars and planetary systems, invisible to the naked eye, detectable only through specialized observations, part of the galaxy's quiet majority, the most fundamental of the forgotten, the medium in which all the other forgotten objects swim. Next time you look up at a night sky and see the stars, know that the spaces between them are not empty. They are filled with gas at temperatures from millions of degrees down to just above absolute zero. They are threaded with dust grains coated with ice and organic molecules. They are the substrate from which new stars and planets will eventually form. They are the archive of the galaxy's chemical history. The spaces between the stars are as full of meaning as the stars themselves, more full in terms of chemical complexity and future possibility. Simply quieter, simply less visible, simply, in the most literal sense, between things rather than being a thing itself. Breathe in the thought of that. The air in your lungs is a thin, warm echo of the cold gas between stars. The carbon in your body was once part of the interstellar medium. You are, in a very physical sense, made of the forgotten. The interstellar medium is also a place of extraordinary violence when viewed on the right time scales. When a massive star ends its life in a supernova, the explosion sends a shock wave outward at thousands of kilometers per second. That shock wave plows into the surrounding interstellar medium, sweeping up gas and compressing it and heating it to millions of degrees. The hot bubble expands, driven by the pressure of the shock-heated gas, carving an enormous cavity in the surrounding medium. The walls of that cavity are compressed and cooled, forming a dense shell of gas that, over millions of years, may itself become gravitationally unstable and collapse into new clouds, new star-forming regions, new generations of stars. So the death of one star triggers, in a very real physical sense, the birth of others. The violence of the supernova is not simply destruction. It is redistribution. It takes the material of the dead star and the surrounding gas and mixes them together, enriching the medium with heavy elements, compressing it into new configurations, setting in motion the processes that will eventually produce new stars and new planetary systems. The interstellar medium is the medium through which the universe recycles its stellar material, the place where old stars become new ones, the quiet background in which the drama of stellar birth and death is embedded. When you look at the night sky and see a dense field of stars in the plane of the Milky Way, you are looking through this medium. Your line of sight passes through clouds of gas at many different temperatures and densities, through regions where supernovae have recently carved bubbles of hot gas, through dense molecular clouds where new stars are forming this very moment, through the diffuse, warm medium that connects all these structures, and through the cold, thin background of gas that constitutes most of the volume. The medium is not empty. It is layered, structured, chemically rich, physically complex, and it is completely invisible to the naked eye. That invisibility does not diminish its importance. The interstellar medium is the galaxy's connective tissue, the material that links the individual stars to the larger structure of the galaxy, the substrate from which all stars form and to which all stars eventually return. It is the most forgotten component of the most studied structure in astronomy. And it is, in its quiet way, indispensable. There is a history behind the forgetting of these objects, and it is worth tracing that history tonight, not to assign blame or to suggest that past astronomers were careless, but because understanding why we forgot something often tells us something important about how knowledge grows and how the limits of our tools shape the limits of our understanding. Every one of the forgotten objects we have visited tonight was not forgotten by accident. It was forgotten for reasons rooted in physics and technology, and the very reasonable human habit of studying what is easiest to study. The earliest astronomers had only their eyes, and the eye, that remarkable organ that evolution has refined over hundreds of millions of years, is exquisitely sensitive to light in a particular range of wavelengths, the visible spectrum, the wavelengths between roughly 400 and 700 nanometers that we experience as color. The eye is not sensitive to infrared light, which is associated with warmth rather than visible brightness. It is not sensitive to radio waves. It is not sensitive to X-rays or gamma rays. And so, for most of human history, the entire accessible universe was the universe of visible light. Brown dwarfs are not visible in visible light. They are far too cool to emit significant amounts of light in the optical range. They radiate in the near-infrared and the mid-infrared, wavelengths that human eyes cannot detect. Even the warmest, most recently formed brown dwarfs, those still glowing from the heat of their formation, are far too dim in visible light to have been detected without the sensitive infrared detectors that were not developed until the latter half of the 20th century. The brown dwarfs were not hidden from us by any perversity of the universe. They were hidden from us because we were looking with the wrong kind of eyes. The same is true of rogue planets. A rogue planet emits no visible light of its own and reflects no starlight since it has no star to reflect. It is detectable only through its gravitational effects on light from distant background stars, the microlensing technique, or in principle through the faint infrared glow of its own internal heat. Both of these detection methods require technology and survey strategies that were not available until recently. The rogue planets were not forgotten because astronomers decided they were unimportant. They were forgotten because the tools to find them did not yet exist. Dark galaxies and the ultra-diffuse galaxies that are their near relatives are invisible in surveys that look for surface brightness above a certain threshold. The techniques and instruments needed to detect very low surface brightness structures require not just sensitive detectors, but also careful attention to removing systematic artifacts in images. Effects like scattered light from bright stars and optical reflections within the telescope that can easily mimic or mask the faint glow of a diffuse object. For much of the history of extragalactic astronomy, these technical challenges meant that galaxies below a certain surface brightness were simply not detectable. The surveys found what they were capable of finding, and what they could not find was assumed to be rare or absent. The history of astronomy is, in part, a history of realizing that what our current instruments cannot find is not the same as what does not exist. Every improvement in sensitivity, every extension of detectable wavelength range, every new technique for removing systematic errors from data has revealed a new population of objects that were there all along, but simply beyond the reach of previous methods. The infrared revolution of the 20th century revealed brown dwarfs and the cold gas between stars. The radio astronomy revolution revealed the hydrogen clouds and the molecular gas and the pulsars. The X-ray astronomy revolution revealed the hot interstellar medium and the neutron star remnants and the intracluster gas of galaxy clusters. The gravitational microlensing surveys revealed the rogue planet population. The low-surface brightness imaging revolution is revealing the dark and ultra-diffuse galaxies. Each of these revolutions has added a new layer of objects to our census of the universe. Each has expanded the known population of things, and usually in the direction of more things. Not fewer, more objects, not less. A fuller and more populated cosmos than the previous census suggested. This pattern of each new instrument finding a new overlooked majority is one of the strongest hints that the universe is far richer and more populated than our current best picture suggests. The forgotten objects we have discussed tonight are the ones we have already found. How many more are waiting for instruments we have not yet built? There is a particular kind of scientific humility that comes from tracing this history. It is not the humility of inadequacy, not the feeling that we will never understand anything because our instruments are always limited. It is the humility of honest proportion, the recognition that what we know is real and valuable, and also that it is a subset of what is. That the map we have drawn, however detailed and however carefully constructed, is not the territory. That the universe is always larger and more varied and more populated than our current picture, and that the appropriate response to this is not despair but curiosity. Every forgotten object that was eventually found was found because someone decided to look. Because someone built a new instrument, or pointed an existing instrument in a direction no one had thought to point it before, or developed a new analysis technique that could extract a signal from data that had previously seemed to contain nothing. Every discovery of a forgotten category of objects is a story of deliberate curiosity, overcoming the comfortable assumption that what was already known was sufficient. The astronomers who first found pulsars were not looking for them. The signal appeared in their data as a mystery, something unexpected that did not fit any known object, and they followed the mystery until they understood it. The researchers who discovered the first confirmed brown dwarf were searching specifically for objects that theory predicted should exist, but that had never been found. They looked because the mathematics said something should be there, even though the observation was difficult. The teams working on low-surface brightness imaging developed new techniques specifically because they suspected that the standard surveys were missing something, that the ultra-diffuse galaxies must exist even though no one had seen them. Curiosity, theory, and new instruments working together have found the forgotten objects one by one. The brown dwarfs, the rogue planets, the dark galaxies, the intracluster stars, the cold gas, the neutron stars. Each one was in some sense predicted before it was found, either by theoretical reasoning or by the growing awareness that something was missing from the census. And each time a predicted object was found, the universe was confirmed as richer and more varied than the previous picture had suggested. This is perhaps the most hopeful aspect of the forgotten objects. They are not a story of permanent ignorance. They are a story of growing knowledge, of a census that is slowly becoming more complete, of a universe that, with each new instrument and each new technique, reveals itself to be more abundant and more complex and more quietly populated than we had known. The forgetting is not permanent. It is a temporary condition of limited technology and limited attention. And as both improve, the forgotten become remembered, one category at a time. The universe has been keeping its inventory quiet, but science is learning, slowly and persistently, to read it. And every forgotten object that is found is not a correction to our picture of the universe. It is an enrichment, an addition, a fuller accounting of what is actually there. That is a genuinely beautiful thing. A cosmos that rewards curiosity with abundance. That yields to every new way of looking, a new population of things that were always there. The forgotten objects are not a rebuke to our limited vision. They are an invitation to keep looking. There is something else worth saying about the history of overlooking. When we look back at the moments in astronomical history when a new population of objects was discovered, what we often find is that the discovery was preceded by a period of theoretical prediction, a moment when someone sat down with the known laws of physics and said, given what we know about how the universe works, there should be objects of this type. We have not found them yet, but they should be there. This is exactly what happened with brown dwarfs. The theoretical framework for objects below the hydrogen burning limit was worked out decades before the first confirmed brown dwarf was found. Astronomers knew what they were looking for. They knew the physical conditions that would produce such an object. They even had a rough sense of how many should exist, based on the known distribution of stellar masses. What they lacked was not knowledge, but instruments. The infrared sensitivity needed to detect these cool, dim objects did not exist at the time the theory was developed. It took the development of sensitive infrared arrays and careful dedicated surveys before the first confirmed brown dwarf could be announced. Theory ran ahead of observation, as it often does in science. And in the gap between prediction and confirmation, the brown dwarfs existed, patient and oblivious, going about their slow cooling in the spaces around our solar system, waiting for human technology to catch up with human theory. They did not know they were expected. They did not know they were predicted. They simply were, as they had been for billions of years, as they would have continued to be even if we had never looked for them. The universe does not arrange itself to suit our theories, but it does, in a deep sense, follow rules that our theories can describe. And when we use those rules honestly, when we follow the physics wherever it leads rather than stopping at the boundary of what is convenient to find, we discover that the universe is both exactly as the physics predicts and far richer than any single application of that physics can capture. The forgotten objects were all predicted before they were found. And after they were found, they turned out to be exactly what the physics said they should be. The universe is consistent. It honors its own rules. And those rules, applied honestly, always point toward more than we have already seen. We have been thinking about the forgotten objects as they exist now, in the present epoch of the universe. A universe that is roughly 14 billion years old, and that is, in the context of the full sweep of cosmic time, still quite young. The bright stars we see in the sky are living out their main sequence lives. The galaxy is still actively forming new stars from its gas reserves. The universe is still full of structure, still rich with galaxies and clusters and filaments. It is, cosmically speaking, an interesting and lively time. But the forgotten objects invite us to think beyond this present moment, because one of the things that makes them different from the bright stars is their relationship with time. The bright stars burn briefly and dramatically. The forgotten objects persist quietly and almost indefinitely. And if we follow that contrast to its logical conclusion into the far future of the universe, we find that the forgotten objects do not merely outnumber the bright ones now. They will come to completely dominate a universe so old that all the bright stars have burned out. Let us take a slow walk into that future. Not a frightening walk, not a morbid one. Simply an honest extension of the physics we have been discussing into the time scales that the forgotten objects inhabit naturally. In the near future, by which I mean the next few billion years, the universe will look broadly similar to how it looks now. Stars will continue to form and burn. New generations of brown dwarfs will be produced alongside the new stars. More rogue planets will be ejected by the gravitational dynamics of new planetary systems. The galaxy will continue to evolve, to absorb its satellite galaxies, to drift toward Andromeda, eventually to merge with Andromeda in a collision that will reshape both galaxies over hundreds of millions of years. The cosmic web will continue to evolve, clusters accreting more mass, voids expanding as the universal expansion carries structure apart. But in the far future, on time scales of hundreds of billions of years, the story changes. As the universe expands and the gas reserves in galaxies are consumed by star formation or dispersed by stellar feedback, the rate of new star formation will slow and eventually cease. The last stars to form will be the smallest and dimmest, the red dwarf stars that burn their hydrogen so slowly that they can shine for 1 trillion years. For a very long time after the last massive stars have died, the red dwarfs will keep the galaxy lit, faint and red, a dim ember glow compared to the brilliance of the present. During this epoch, the forgotten objects will accumulate. Every star that completes its main sequence life will leave behind a remnant. The massive stars, already long gone by this point, will have left neutron stars and black holes. The intermediate stars will have left white dwarfs, and the red dwarfs, when they finally exhaust their fuel trillions of years from now, will leave behind white dwarfs as well. Slowly, the population of white dwarfs will grow, accumulating over hundreds of billions and then trillions of years, until eventually the galaxy contains far more white dwarfs than stars. a collection of cooling embers gradually outnumbering the fires. The brown dwarfs will still be there. They cool so slowly that the brown dwarfs forming today will still be recognizable as brown dwarfs trillions of years from now, dim and cold, but still warmer than the surrounding space, still carrying their internal heat, still floating with their iron clouds and methane atmospheres, persisting through epochs in which every true star born today has long since died. The patience of the brown dwarf is one of the most extraordinary facts in all of astrophysics. An object that never ignited will outlast, by an enormous margin, all the objects that did. Further into the future still, on time scales so vast that they make the current age of the universe look like an eye blink, the white dwarfs will cool toward their eventual darkness. One by one, over quadrillions of years, the white dwarfs will reach the temperature of the surrounding space and become black dwarfs. Dark, cold, crystalline spheres of compressed carbon and oxygen, drifting in a galaxy that has by this point lost almost all its original stellar light. The galaxy of the far future will be a collection of black dwarfs and neutron stars and black holes and brown dwarfs and rogue planets, all drifting through a space that is darker and colder than anything in the present universe. The rogue planets will still be drifting. They will still be there, those wandering worlds that were ejected billions or trillions of years before. They will be colder, their geological activity long since ceased, their interiors frozen completely. But they will still be there, moving through the galaxy, following their long arcs, carrying within their rock and ice the frozen chemistry of their origins. Patient beyond all patience, persistent beyond all persistence. The intergalactic stars will still be burning, for as long as they are stars at all, in the voids between galaxy clusters. But eventually, they too will exhaust their fuel. The longest-lived ones, the small red dwarfs that were flung into intergalactic space, will burn for trillions of years in the void, their light traveling for tens or hundreds of millions of light years, without reaching anything before they too go dim and leave behind their white dwarf remnants. Even the most isolated stars in the universe will eventually join the quiet population of cooling remnants. What does the universe look like in that far future? It is a strange and quiet place. The cosmic web is still there, in a sense, but so spread out by the accelerating expansion that the clusters and filaments are separated by distances so vast that the light from one cluster will never reach another. Each cluster will be effectively alone in its own observable universe, isolated by the expansion from all other structures. And within each cluster, a collection of cold, dark, slowly drifting objects, the remnants of billions of years of stellar evolution, the forgotten objects that outlasted everything else. No supernovae, no blazing quasars, no hot young stars illuminating nebulae in blue and pink, no galaxy collisions spraying streams of stars across intergalactic space. Just the patient remnants, the quiet majority of the distant future, drifting in a cold and dark and almost featureless cosmos. And this is the destination toward which the universe is heading, not now, not for an almost incomprehensibly long time, but eventually. The universe's future belongs to the forgotten objects. The bright stars are a temporary phenomenon, a feature of the universe's youth, a few trillion years of brilliant activity bookended on both sides by a vastly longer quiet. Before the first stars formed, the universe was dark and cool and structureless. After the last stars die, the universe will be dark and cool and populated only by the quiet remnants of the stellar era. The forgotten objects are not only the universe's quiet majority at present. They are the universe's destiny, The patience of the brown dwarf and the white dwarf and the rogue planet and the neutron star is not a temporary condition. It is a preview of what the universe becomes on the largest time scales. The present epoch of blazing stars and dramatic events is the exception. The quiet, cold, drifting abundance of the forgotten is the rule. Let that thought rest in you gently, not as something frightening, not as a picture of death or decay, but as a picture of the universe's extraordinary patience, its willingness to produce complex, interesting objects and then let them persist quietly, unchanging for time scales that make the current age of the universe seem brief. The universe is not in a hurry. It has quadrillions of years to spend in the quiet company of its forgotten objects. And in that long, quiet time, who knows what rearrangements, what new processes, what forms of complexity might arise that we cannot now imagine. The far future of the universe is not empty. It is populated by the patient remnants of the present. The forgotten objects of today are the inheritors of tomorrow, and their quiet abundance will persist long after the last bright star has faded from the last galaxy's sky. The thought of deep time and the future of the forgotten objects can feel, at first, like a melancholy one. A universe growing darker and colder, stars exhausting their fuel, galaxies spreading apart until they are isolated from each other by the accelerating expansion. The eventual darkness of a cosmos populated only by cooling remnants and drifting worlds. If you hold that picture with a focus on loss, it can feel heavy. But there is another way to hold it. Consider that the universe in its patience is not ending. It is changing. The stellar era, the 10 trillion or so years during which stars burn and galaxies shine, is one chapter in a much longer story. What comes after, the long dark era of remnants and rogue planets and black dwarfs, is not an ending but a continuation. A different kind of existence, quieter and darker, but not nothing. The forgotten objects are not the residue of a universe winding down. They are the form the universe takes when it has finished one phase of its existence and entered another. The patience of the brown dwarf and the white dwarf is not the patience of objects waiting for something to happen. It is the patience of objects that have settled into their proper condition, that exist in the mode most natural to the physics that governs them, that persist because persistence is what the laws of nature allow and require of them. In the deepest sense, the universe's trend toward quiet abundance is not a story of loss. It is a story of settling, of the cosmos finding its natural equilibrium. The stars are a transient feature of a universe that was briefly hot and dense enough to sustain them. The quiet objects are the universe's natural state, before the stars and after them. In between, for a few trillion years, the universe blazes. But the long epochs on either side belong to the quiet, the cold, the patient, the dark. And in that long quiet, in the universe of cooling remnants and drifting worlds, what might still be possible? We cannot know. Physics tells us what happens to matter at low temperatures and low densities. But physics does not tell us whether some new form of complexity might arise in conditions so different from the present that we cannot currently imagine the processes that might occur. The universe's deep future is genuinely unknown, and unknown futures are, in their way, full of possibility. Rest with that thought. The forgotten objects drift toward a future that even science cannot fully see. Patient, persistent, quietly abundant. Part of a universe that is not ending but changing. Moving toward a different kind of existence that has its own kind of meaning. There is one more thing worth sitting with tonight before we let the journey end completely. It is perhaps the strangest and most personal of all the ideas we have touched on. We have talked about the forgotten objects as though we were observers looking in from outside. As though we were tourists visiting a museum of overlooked things, appreciating each exhibit and then moving on. But we are not outside. We are inside. We are part of the same universe that contains all these quiet, drifting, invisible things. And the fact that we can know about them, that consciousness of any kind can exist in a universe that is primarily cold and dark and quiet, is itself one of the most remarkable facts we have encountered tonight. The universe, as we have established, is primarily made of things that do not notice anything. Dark matter does not notice the galaxies it scaffolds. Rogue planets do not notice the interstellar gas they drift through. Brown dwarfs do not notice the stars they resemble but never became. Neutron stars do not notice the extraordinary density of their own interiors. White dwarfs do not notice the slow crystallization of their carbon and oxygen. The cold molecular gas between the stars does not notice the organic molecules forming in its depths. The intergalactic stars do not notice the millions of light years of void their light crosses before reaching anything. None of these objects notices anything. They simply are. They proceed according to physics, following the laws of gravity and electromagnetism, and nuclear force and thermodynamics, without any awareness of what they are doing or what they are part of. The universe's vast quiet majority is, as far as we can tell, entirely without experience, entirely without observation. Simply present, simply real, simply drifting or burning or cooling in the dark. And yet, here we are, on a small rocky planet orbiting a modest star, made of the same atoms as all those quiet objects, following the same physical laws, part of the same universe. And we notice. We build instruments and develop theories and point telescopes at faint corners of the sky and tease out the signal of a brown dwarf's infrared glow or the brief brightening of a microlensing event that reveals a rogue planet's passage. We ask what is there, and we find things. We ask why things are the way they are, and we build explanations that allow us to predict what else should be there before we have found it. We develop a kind of awareness of the universe's contents that extends, in principle, to every object in the observable cosmos. This is not a small thing. In a universe that is primarily unconscious, primarily dark, primarily drifting, the emergence of anything that can notice the universe is an extraordinary event. Not miraculous in the supernatural sense, but remarkable in the physical sense. Consciousness, whatever it ultimately is a process that requires an astonishing amount of structural complexity. It requires a planet with the right conditions, a chemistry that can produce self-replicating molecules, an evolutionary process that selects for increasing complexity, and eventually for the kind of nervous system that can model the world around it. It requires billions of years of stellar evolution to produce the heavy elements that make rocky planets possible. It requires those planets to form in the habitable zones of stable stars. It requires the long, patient work of evolution to produce organisms complex enough to wonder. All of this, the entire chain from the Big Bang to the first atoms to the first stars, to the first heavy elements scattered by supernovae, to the formation of rocky planets, to the emergence of life, to the evolution of consciousness. All of it was necessary before any part of the universe could begin to notice the rest of it. The universe had to become very old and very complex before it could look at itself. And when it finally did, when consciousness arrived in whatever form it first took on whatever world it first appeared, the universe did not become aware of itself completely. It became aware of itself in one small place, through one small window. Everything that consciousness has ever learned about the universe, every observation and every theory and every insight, has been gathered from a single tiny vantage point. A planet around a star in a galaxy, in a cluster, in a supercluster. One location among the countless possible locations from which the universe might be observed. And from that single location, through the remarkable and hard-won tools of science, we have managed to discover the quiet majority. To find the brown dwarfs and the rogue planets and the dark galaxies and the intergalactic stars and the cooling remnants. To map the dark matter through its gravitational effects. To detect the dark energy through its effect on the expansion of space. To reach outward from that single small vantage point and build a picture of the cosmos that extends to the edge of the observable universe in every direction. That picture is incomplete. It is, as we have seen tonight, dominated by things we can barely see, by quantities we cannot directly detect, by objects whose populations we can only estimate. But it is a picture, a genuine and increasingly detailed portrait of what exists, built from the patient accumulation of observations and the creative development of theory over centuries of scientific inquiry. And every time that picture is expanded, every time a new instrument finds a new population of forgotten objects, the universe becomes more real to us. Not more imaginary, not more abstract, but more real. The brown dwarfs that were unknown to our grandparents are now mapped in our cosmic backyard. The rogue planets that were theoretical predictions a generation ago are now confirmed as one of the galaxy's most abundant populations. The dark galaxies that were invisible to every astronomer before a decade or two ago are now known to drift in their hundreds in galaxy clusters all around us. Each expansion of the known is an expansion of the universe's self-awareness. Each forgotten object that is remembered is a piece of the universe understanding itself more completely through the minds of the beings it has produced. This is, I think, the deepest wonder of the forgotten objects. Not simply that they exist, though that is wonderful. Not simply that they are so numerous, though that is humbling, but that they can be found, that the universe has produced, among its vast quiet majority of drifting and cooling and unconscious things, a tiny minority of conscious beings capable of reaching out and finding the quiet majority, of building the instruments and the theories and the surveys that turn the invisible into the known, of remembering the forgotten. You are part of that tiny conscious minority. Tonight you have spent time with the forgotten objects. You have given them your attention, and in doing so, you have participated in something that the universe has been working toward for almost 14 billion years. The slow, patient, accumulating process of the cosmos noticing itself. It is a very small contribution, one mind resting with the image of a brown dwarf or a rogue planet or a dark galaxy for a few quiet minutes on one night. But it is real. It is part of the same process that drives the scientists to build better instruments and the theorists to develop more complete models. The wonder is the same whether it fills a research paper or a quiet moment before sleep. The universe is equally well noticed. Let the quiet settle around that thought. You are a temporary arrangement of atoms that were once in stars. You exist in a vast, mostly dark, mostly quiet universe that is far fuller than it appears. And tonight, for a little while, you notice some of what is there. The brown dwarfs drifting in the local dark, the rogue planets crossing the galaxy alone, the orphaned moons carrying their frozen archives, the dark galaxies vast and ghostly in their clusters, the intergalactic stars burning for billions of years in the void, the white dwarfs cooling toward their crystal darkness, the neutron stars spinning in their extraordinary density, the cold gas between the stars carrying its organic chemistry. The whole quiet, patient, abundant, drifting majority of a cosmos that mostly does not notice itself. You noticed. That is enough, more than enough. It is, in the context of the universe's mostly unconscious existence, something close to extraordinary. Rest now in the awareness of the quiet majority. The forgotten objects drift on, and you, briefly conscious, briefly noticing, briefly here, are part of the same universe. Small, real, and present, just like them.